Hello, good evening, my dear lovely lions. Welcome aboard to the Vedantu NEET English channel. This is your Captain Shreyas. And in the NCERT line by line series, today we are doing the part 2 of Electrostatic Potential and Capacitance, which is the chapter number 2 from your NCERT. And like I have said before, NCERT line by line series is a series where we decode, understand all the hidden things and all the complicated terminologies or paragraphs which are there in NCERT in a very simple manner, and this will 100% help you in your NEET as well as board examinations. Like I have said before, that NCERT has close to around 40 to 60% weightage, depending on subject to subject, and it plays a very crucial role in laying your foundation and also gathering all that information where NTA will ask the exam questions from. So all the serious NEET aspirants, use these series to the fullest of your knowledge, and this is your Captain Shreyas, your mentor, your guide, yes, who is going to help you throughout this journey. So make sure you are subscribed on the channel so that you do not miss any of my classes. Number 2, make sure you are liking the video to show your full support, because this is the first time in history you are seeing NCERT decoded in English medium. Okay? So thank you so much. Hello Krishna, hello Sukanya, hello Pratibha. Happy Janmashtami Krishna. Wow, it feels so nice to congratulate you or to wish you on Janmashtami. It feels like very divine. Yep. And those of you who have missed the previous lecture, let me just show it to you. If you go to the live section of our Vedantu NEET English channel, you will see that we have done this part 1 just few days back, electrostatic potential and capacitance. So today we are doing the part number 2. Okay, and yes, this is the part number 2 which we are doing right now. And let me also remind you, in the pinned messages as well as the description box, first of all quickly like the video guys in case you have forgotten. The description box, there is a link for joining our test series which are available in 3 different modes in case you are not aware. Yep, one is the online test series. The second one is offline, where the test papers are couriered to you. And the third one is offline, where you go to the center and give the test. A set of 25 tests which are prepared freshly with solutions, with proper discussions and everything that you need for your upcoming NEET preparation. It has part tests, chapter tests, full syllabus tests, NCERT based tests, which will take you to a different level, especially even if you are already enrolled in a coaching. I feel having a different perspective of the questions helps you a lot. So if you have not yet checked this test series out, do check it out, because it is at a very affordable price, starting off at 999 rupees, and even the offline where you get the OMR sheets as well couriered to your home address at 1999. All right. So let's begin with the class, and make sure you are using the test series to the fullest. Hello G Star. Hello. Good afternoon, good evening, Madhumati, actually. Yeah, so we have done all these things right from 2.1. You can see all these things were done just a couple of days back. This was part 1. Let me just quickly go through all the main slides over here. We did about potential, how it was defined, work done per unit charge, the potential due to a point charge we have done. Then we have also done how to find the potential due to dipole on different points. We have also then see potential of a sphere inside, outside, equipotential lines, right? All these things we have seen, and what are the different properties of equipotential lines. Okay. Then we have also seen relation between field and potential, which is minus dV by dr. We have also seen calculating the potential energy of a system by adding up all the energies of each pair. That is what we have done till now. So now we have also done this is done. Okay, so I think we should now go to electrostatics of conductors. Okay, so this is the part which we are going to do, and then we will slowly go till capacitors. Okay, slowly we'll go till capacitors. So let's begin with the lecture. Okay, so let's go through this slowly. Conductors and insulators were described in chapter 1. Remember, conductors were those elements which can freely give the electrons to conduct electricity. That means the flow of electrons forms current, and that happens because the electrons are free to move, and the electrons always choose to move because of the force acting on them because of the battery or the voltage difference which is connected across the conductor. Insulators do not allow the flow because they do not have free electrons as such. Okay, these electrons are free within the metal but not free to leave the metal. The free electrons kind of a gas, they collide with each other, blah blah blah. In an external field, they drift against the direction of the field. The positive ions made up of the nuclei and the bonded electrons mainly held in the position. The electrolytic conductors, the charge carriers are both positive and negative. The situation in this case is more involved. The movement of the charges carriers are affected by both external electric field as also by the so-called chemical forces. We shall restrict our discussion to metallic solid conductors. Let's see our important results. In this thing, we don't have much anything important, but mainly you should know about conductors and insulators. Conductors versus basically insulators. We have already studied all the important properties of conductors which contain mobile charge carriers, and usually they are metallic in nature. Okay, and all that was already done in chapter 1. So it's just a recollection of that. You know how electrons are available freely for conduction, and another way in which electricity can be conducted is through electrolytes, where you see cations, anions being formed, and these cation anions also can move inside that electrolytic fluid. But that is just for namesake that is mentioned here. You study that in electrolysis chapter in chemistry or electrochemistry. In physics, you don't deal about it much, but just that you have an idea. Okay, there are different things which can conduct electricity. It's not necessarily metals, but you also have electrolytes also. That is just for mentioning purpose, but you don't have to study that over here. Now, let's go to the more physics part of it. Okay, let's go to the more physics part of it. Hello, Chitra. Good evening, my dear warriors. Join in. In case you are a little bit late, it's okay. Just join in. I know usually my lecture timing is 6 o'clock. I had to shift it at 4 o'clock because of Janmashtami. So that's the reason, because there are some things which are involved in the evening. Okay, cool. Now, inside a conductor, electric field, electrostatic field is 0. Consider a conductor neutral or charged. There may be external electrostatic field. In the static situation, when there is no current inside or on the surface of the conductor, the electric field is 0 everywhere inside the conductor. This fact can be taken as a defining property of a conductor. A conductor has free electrons. As long as the field is not 0, the free charge would experience force and drift. In static situation, the free charges have so distributed themselves that the field is 0 everywhere inside and the electrostatic field inside is 0. Okay, I'll explain this to you. Now, imagine, my dear students, imagine that let's say this is a conductor. Imagine this is a conductor, okay? And on this conductor, there are some charges over here. Let's say there are some charges involved over here, and let's show the charges somewhere. Maybe there is one charge here, maybe there is one charge here, 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 one charge here, one charge here. So called, this is the distribution of the charges. Now just imagine you are somewhere inside this conductor. Let's say you take a point here. Let's say you take a point here. What will happen? This charge will develop an electric field like this. This charge will develop an electric field like this. This will develop electric field. 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 Does it look like the electric field is cancelling in this situation? Does it look like the fields are perfectly cancelling each other? I don't think so. I can see more or less the field is concentrated somewhere down. So they are not cancelling each other. I can clearly see that there is a resultant electric field at any point over here. So 100% there is a net electric field, and this net electric field is not 0. Now in this situation, what will happen? Imagine you have an electron somewhere over here. You have a charge. You have a free charge over here. Imagine you have a free charge over here. What will that free charge experience? What will that free charge experience? Obviously, that free charge will experience some net force. There will be some net force on that charge. Because of that, what will happen? There will be motion of the charge. The charge will start moving. Once the charge starts moving, what does it mean? It just means that there is current inside that conductor. There is current inside that conductor. Just imagine you take a conductor. It is not connected to any battery, any wire, any potential difference. Just you take a conductor and imagine there is current flowing inside the conductor. You will be like, sir, this is a free source of energy, sir. I just take a conductor and magically current is flowing inside of it. This violates any principle of conservation of energy. 100%. Just think about it. Or else people will carry in their pockets small conductors which are charged. It is generating magically current. It can charge your phone. It can run your fan. It can light a bulb. It can run your AC. That cannot happen. Magical source of energy it will be. So, this distribution of charges was creating a field which was creating a force which moved those charges which are free inside this conductor, which made up the current, which is not possible. This is basically not possible at all. This is not possible at all. So what should be possible is this, where you have a conductor, the charges distribute in such a way, the charges on it distribute in such a way that, everywhere you see, no matter where you go inside this particular conductor, everywhere, this point, everywhere, you should see that the net electric field is zero. If the net electric field is zero, what does it imply? That the net force is zero on any charge carrier, on any basically charge carriers, on any charge carriers. Hence, what can I say? Hence, there is no current which is set up, which is exactly what you expect. If you have a conductor, that's it. There is no current inside it. It's just charge. It is a static scenario. So that's why these charges will then be referred to as static charges. Static charges on the conductor. Static charges on that particular conductor. Do you guys agree with this now? What happens inside a conductor? Interesting, isn't it? So this is what should happen. This is not possible. This situation is not possible. Understand that. This is not possible. This is wrong. This is correct. This is possible. This is exactly what happens. This is what happens. That is what they have mentioned in this particular paragraph. So let's highlight the important points. In static situation, when there is no current inside, very important, or on the surface of the conductor, the electric field is zero everywhere. The electric field is zero everywhere inside the conductor. This is the most important line as takeaway. Okay, this fact can be taken as a defining property of a conductor. The conductor has free electrons. They have explained it why it is so. Okay, so electrostatic field is zero inside a conductor. As simple as that. It's the same thing they have repeated. Like I said, NCERT is like, that middle bencher or back bencher who has to write a 4-mark question, but, they are having, some knowledge and they want to just fill up the pages. Just look at it. Inside a conductor, electric field is zero. Electric field is zero everywhere inside the conductor. Electric field is zero inside a conductor. In one small thing, they have repeated the same thing 3 times. So you will see a lot of repetitions. Just don't, again sir, this is important sir, they have made it into italics. I will highlight this also. Sir, heading is also important, highlight this. Don't do all such things. You have written it, you have highlighted it once, no, enough. Don't have to highlight it 100 times just because it looks important. It's the same thing. Chumma writing the same thing again and again. Got it, everyone? Okay. How many of you do this? 4-mark question, writing the same thing again and again. Okay. Here also they will have done the same thing. Let's see. Okay, again they will. At the surface of a charged conductor, electric field must be normal to the surface at every point. If E were not normal to the surface, it would have some non-zero component. Free charges on the surface of the conductor would then experience in the static situation. Therefore, E should have no tangential component. Thus, the electrostatic field on the surface of a conductor must be normal to the surface at every point. See, tell me one thing. I am good is the same as saying I am not bad. Right? I am smart is as good as saying I am not dumb. So, just think about it. Electric field, they are saying if I take a electrostatic field, if I take a conductor, this is a conductor, guys. They are saying on the surface of the conductor, it is basically normal. It is basically perpendicular. That is what they are saying. That means there is no tangential component. Along the tangent, there is no component. Same thing. Hence, there should not be any tangential component. Again, they repeat it. Thus, the field at every point is normal. How many times will you say the same thing, guys? I mean, like, really. But still, I'll highlight only the important thing. The electric field at the surface of a charged conductor must be normal to the surface at every single point. Hence, the electric field should not have any tangential component. It means no matter where you go, you will probably see the electric field lines probably going like this, maybe going like this, maybe going like this, maybe going like this, maybe going like this. Oops. Everywhere they are perpendicular to the surface of that particular conductor. That's what it is. Inside, remember, electric field inside was anyway zero. It's only outside which it is perpendicular. It can't have tangential components. This is the second property. You will be like, sir, why is it so? Why is it that there cannot be any tangential component? Let's assume that the electric field is not perpendicular, rather electric field is making some angle. So then the electric field will have two components, one component which is perpendicular and the other component which is basically tangential. Electric field which is tangential. Let's assume over here some angle is made by the electric field inside that particular conductor. So then what will happen, because of this tangential component, you will see that those charges which are there, those free charges which are there, those free charges will now experience a force, because of which there will be motion along the surface. Of the conductor. And if there is motion along the surface of the conductor, that means there is nothing but surface current. How is it possible that you take a conductor and on the surface magically current is flowing? Just imagine, I take a lump of conductor which is charged, zoom, 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 conductor, the current is flowing on the surface. It will be like a very important stone. It will be like a very important piece of conductor. Everybody would want such a conductor. They will store it in their houses. They will carry it everywhere, because then if you have magical currents, it is like a infinite source of energy. Not possible at all. Law of conservation of energy can't be violated. So this is not possible. Is what they have basically explained. This is not possible. What happens in reality is just this: there is no tangential component, only electric fields are perpendicular. It would be magic. Yes, correct. That is the second statement. Third one, the interior of a conductor can have no excess charge in the static situation. A neutral conductor has equal amounts of positive and negative charges in very small volume or surface element. When the conductor is charged, the excess charge can reside only on the surface of the static situation. This follows from the Gauss law. Consider an arbitrary element inside the conductor. On the closed surface bounding the volume, the field is zero. Thus, the total flux should be zero in that surface. Hence, by Gauss's law, there is no net charge enclosed by it, but the surface S is made of small as possible. The volume V can be made vanishingly small. This means there is no net charge at any point inside the conductor, and any excess charge must reside on the surface. They have repeated many statements. I'll explain this to you in a very simple way. Okay, let's take. Imagine a conductor again over here. Imagine that there is a conductor over here, and you charge that particular conductor. Imagine you are charging that particular conductor. When you charge that particular conductor, usually what should happen is the charges should be only on the surface of that conductor. it can't reside anywhere inside. The interior of a conductor cannot have any excess charge. See, if you take anything, be it insulator, conductor, semiconductor, it has atoms, it has molecules, equal number of protons and electrons are there. But when protons are more, you said that it is positively charged. When electrons are more, you say that it is negatively charged. So one thing is in excess as compared to the other. That's when you say the body is charged. Otherwise, they have both positive, negative charges. Now, that excess charge which is there, that additional charge which is there, okay, where does it stay? Madhumati, sorry, who is it? Rakshana, did I change my hairstyle? I don't know, bacha. I just smooth a brush, whichever way it goes, that is the new style of Captain Shreyas Sir. So, I don't really plan it, it just goes somewhere. Okay, it depends on the mood of my hair. The hair will say, I want to go here, it will go there. That's all. All right. So, yeah, we are just saying that the charges cannot stay inside, that excess charges. So, there is a proof for it. Let's assume the opposite. Just imagine the charges are not only there on the periphery, but also there are some internal charges. Just imagine there are some internal charges also somewhere here. Just assume these are basically our internal charges on that particular conductor. So what they say is, you take a Gaussian surface. What do? You take a Gaussian surface, which is enclosing this particular excess charge. So this is our Gaussian, this is basically our Gaussian surface. And what does Gauss law say? That the net flux of a closed surface, should always be whatever charges are inside divided by epsilon naught. That is your Gauss law. Because this Qin is there, that means there must be net flux from that closed surface. If this is not zero, this should be also not zero. This means that electric field must be there on the Gaussian surface, which I have taken, guys. That means I must agree to this point that this electric field must be there here. But if electric field is there here inside the conductor, it violates this principle that electric field inside a conductor must always be zero. Electric field must be zero. So this is basically not possible. But electric field inside must be zero. Hence, this is not at all possible. This is not possible, guys. This is wrong. So what is possible is this. If you have any conductor, any random shape, doesn't matter. Always the charges must reside on the surface of the conductor, whether it is positive, negative, doesn't matter. These charges are always on the surface, never ever inside. So this is something which is acceptable. Is that absolutely clear, everyone? Everybody understood till this point? So let me highlight this. Has equal amount when the conductor is charged, the excess charge can reside. Okay. So the volume can be, this means that there is no net charge at any point inside the conductor, and any excess charge must reside at the surface. Always the charges are on the surface, never ever inside. It's as simple as that, and that is being proved by your Gauss's law, which I have used right over here. So I used Gauss's law to prove that this situation is not possible. It has to reside outside. Clear? Everyone, shall we go ahead? Awesome. Very good, Krishna, Chitra, Pratibha, Madhumati. Very good, Sukanya. Awesome. Moving on to the next property of the conductor. Electric potential is constant throughout the volume of the conductor and has same value as on the surface. This follows from the results 1 and 2 above. Since E inside of the conductor is 0, there is no component, no work is done, blah blah blah, there is no potential difference. Hence the result, the conductor is charged, field is normal to the surface. This means potential will be different for different surface. Different for the surface and at a point outside the surface in a system of conductors of arbitrary size, shape and charge configuration. Each conductor is characterized by a constant value of potential, but the constant may be different from one conductor to other. Okay, see guys, simple words, I will explain this to you. They write these statements as if they are writing some law book or something, but it is very simple. See, you take any conductor, okay, you take any conductor. Tell me, what is the field inside the conductor? Put it up in the chat box quickly. What is the field inside that particular conductor? Everyone, put it up in the chat box. What is the electric field inside any conductor? What is the electric field inside any conductor? Yup, the electric field inside is basically 0. Everyone, very good. Awesomeness. Yeah, 1 second. Very good. The electric field, whatever it may be, can only exist outside. We have seen that. Electric field can only exist outside. Right? Electric field can only exist outside. We have seen that. And they are perpendicular to the surface. The electric field outside is perpendicular to the surface of our conductor. We have seen that already before, and it is not 0, 100%. Now we also know the relation between electric field and electric potential. Electric field is minus, if you remember, dV by dr. Electric field is minus dV by dr. If by chance I tell you electric field inside is 0, that means dV by dr inside is 0. That means the potential inside, the derivative, if it is 0, that means the function is a constant. That means it is basically a constant, which means all these points are equipotentials. So all these points inside the conductor have the same voltage. So all points inside have the same voltage. Is that absolutely clear, my dear warriors? Yep. So that is what they have mentioned also. The electric field is normal. It means the potential, where have they mentioned? That is, there is no potential difference. Yeah. So I'll just show it over here. That means there is no potential difference between any two points inside or on the surface of that conductor, because the field here everywhere is 0. So no rate of change of voltage. That means voltage is same. But outside we know voltage difference exists, but outside we know electric field exists. That's why voltage difference will exist. So you will see, if you show an equipotential surface, it will probably be like this. Remember, equipotential surface themselves are perpendicular to the electric field. That property we have seen in lecture number 1. So they go like this. And there will be many more such equipotential surfaces of different values. Each one will have different value. This will be V1, V2, V3, etc. These are equipotential surfaces around the conductor, outside of it. So this means potential will be different for the surface and at a point outside the surface. So when you go outside, equipotential surfaces do exist, potential difference does exist outside. That is the meaning of this. Is that absolutely clear? Everyone understood this point? I'm so glad, Suganya, Kunglal, you understood and every single point is absolutely made clear. So here we are decoding NCERT. You will see that there are so many lines which are not important, so many lines which are repetitive, so many lines which could be confusing, but we have to understand the summary which is useful for our NEET or board examinations. And we have to understand the concept behind everything, because that is what is exactly going to be asked by NTA. They are going to keep an NCERT book in the front, they are going to keep some previous year papers, they will have a question bank, and they are going to frame the question paper like that only. Electric field on the surface of the charged conductor is sigma by epsilon naught, and they have done a small derivation for it, and I will show that to you in a bit. Okay, and they have written down the formula also over here. Okay, and let me basically show this derivation in a very simple way. Okay, so guys, I will do the same derivation without just copying it or without just showing you that slide. Imagine we have a conductor like so. Take a conductor like this is our conductor, and we are interested in finding out the electric field on the surface of the conductor, and we all know that electric field on the surface is basically normal. Electric field on the surface is basically normal. It goes something like this. Okay, there could be many more lines, I am not showing it. This is the electric field on the surface. In order to find that out, what we define or what we need is a property called as the surface charge density. Surface charge density. Now, why surface charge density? Because we just saw that electric charges are only on the surface, they are not inside the conductor. We just saw it, isn't it? So that is why we define how much charge is there per unit area. The symbol for that is sigma. So it is nothing but the charge which is there per unit surface area. Per unit surface area. And the unit of such a thing will be obviously coulomb per meter square. Coulomb per meter square. That will be the unit of it. So if you take any patch over here, how much charge is there per unit area is what defines the surface charge density. Now imagine like that, you take a patch, maybe over here, okay, maybe over here. This is a very small area, I'm just zooming onto it, and I know that the electric field lines are there over here like this, perpendicular, okay, in this particular fashion. I know inside of this, which is the inside of the conductor, this is the inside of the conductor, guys. I'm showing it in gray part. It's like you have taken a slice of cake. Everybody has gone to a birthday party and eaten a cake, right? So this is the top part, the chocolatey part, that cream part of that cake. This is that inside part, which is that bready kind of part, or that slightly solidish, or that dry part of that cake. Are you able to visualize it? This is the inside part, this is the surface. Are you able to visualize, my dear students? Okay, clear till this point? Okay, awesome. Now, what I will do, I will take a Gaussian surface. I will take a Gaussian surface. Maybe it involves few of the, okay, this is basically a Gaussian surface, something like this. I'll take it like this. This is my Gaussian surface. When I say Gaussian surface, means any closed surface is called as a Gaussian surface. Now please visualize this, that okay, this is like a three-dimensional diagram. Some of the field lines are piercing out of it, some of the field lines are parallel to it, etc. Are you able to visualize this Gaussian surface, my dear warriors? Are you able to visualize this Gaussian surface? You can see the top surface being penetrated by those electrical field lines. Yep. Awesome. Now, if I apply Gauss's law, which is the flux through any closed surface, is equal to the charge which is inside by epsilon naught. Observe carefully, the charges over here are the charges on the surface. The charges over here are basically the charges on the surface. If I assume this particular area to be A, that orange part, and the charge on it to be Q, the charge on it to be Q, then that Q is the charge which is present on that surface of the conductor, but also inside this Gaussian surface, inside that blue diagram. So that is basically Q, and that epsilon will come here as it is. This flux through the closed surface, remember, electric flux is only counted when the field lines pierce through it. This part, the field lines do not pierce, they are going parallel to it. This part also, there is no field piercing through it. There is only this part where the field is piercing. Remember, inside the conductor, the field is zero. So there is no field from below. There is only field which is coming out like this. Hence, I should definitely say that the flux from the closed surface is only the flux which is coming from the top. The rest all are just zeros. The rest all are just zeros. Do you agree with this statement? Everybody clear till this point? Everybody clear till this point? Very good, Chitra, you are able to imagine. Can we take a cylinder? Yes, you can imagine a cylinder too. Yes, Pratibha, thank you for putting up that cake. Awesome. Awesome. Now, what is this Q? You can observe this from here. This charge is Q. Area is basically nothing but that A. So, from this, can you not see what Q is? What Q is? Q is basically sigma multiplied by that area. This Q is sigma multiplied by that area. So how about just putting that right over here? Is nothing but sigma multiplied by area divided by epsilon naught. This flux on the top surface, the flux on the top surface, flux is field multiplied by area. Flux is field multiplied by area, guys. The electric field is just E. The electric field is just E. You can clearly notice over here that area and area just got cancelled, and therefore I'm getting the electric field as, nothing but sigma by epsilon naught. Sigma by epsilon naught. So this is something which you are supposed to remember. This is something which you are supposed to remember. Is it clear? So this is a definition, or this is a formula of electric field just outside the conductor. This is the electric field which is there just outside that particular conductor. So that is what they have done. Electric field at the surface of the conductor is sigma by epsilon naught. Is sigma by epsilon naught. Understood? Now you might get confused between, sir, sigma by 2 epsilon versus sigma by epsilon, sir. Sir, how do I remember that, sir? See, simple. If you have a sheet, if you have an electrically charged sheet, then the electric field lines will go here also, here also, here also, here also, here also, here also. Whereas when you are talking about a conductor, the electric field is only coming on one side. The electric field is only coming on one side, which is basically outside. There is only one side. Here it is going both the sides. So when it is going only one side, the electric field will be sigma by 1 epsilon naught. Here it is going both sides, so sigma by 2 epsilon naught. Both sides, one side which is outside. You can also say it is getting divided as half. It is half into sigma by epsilon. Sigma by epsilon, half here, half here. You can think of it like that. It's getting divided. So that way you can avoid the confusion between these two formulas. Awesome? Yeah, never ever make this mistake again. So now you know the derivation, how it works. You have visualized this properly, and I showed you this Gaussian surface is any random surface, but in NCERT I think they have taken a cylinder, which need not be always true. You can take any shape, doesn't matter. It doesn't matter. So you just saw that over here. All right, moving on to the next one, which is electrical shielding, and this is a very, very interesting thing. Consider a conductor with cavity, no charges inside the cavity. A remarkable result is that electric field inside the cavity is zero. Whatever be the size and the shape of the cavity and whatever be the charge on the conductor, on the external field might be applied. We have proved a simple case as a result already. The electric field inside is zero. The proof of the result, blah, blah, blah. The vanishing electric field on the cavity is mentioned as above. A very great result. So main important results over here is that remarkable result that electric field inside the cavity is zero, whatever be the size and the shape of the cavity, and whatever be the charge on the conductor and the external fields in which it might be placed. This is the most important line. Okay, now I'll just explain this to you. The proofs of the results are omitted here, but we need to know the important implication. Whatever with the charge, again they say the same thing, guys. Whatever they wrote here, again they're writing it here only. See, whatever be the charge and the field configuration outside the and any cavity inside the conductor remains shielded. Just written it in a different way. So whatever be the charge and the configuration outside, any cavity in a conductor remains shielded from outside electrical influence. The field inside the cavity is always zero. This is also known as electrical shielding. The effect can be made use in protecting sensitive instruments from outside things. Okay, so this is not at all needed. The main takeaway is over here only. So what does this basically mean? Okay, has it ever happened that you don't want to turn off your phone, but you don't want anybody to reach to you? You are very angry, you are very depressed, you are very, demotivated. Has it ever happened to you that, sir, I don't want anybody to call me, sir, I don't feel like talking to anyone, but I don't want anybody to listen, the phone is switched off. It should feel like he's out of coverage or she's out of coverage area. Have you ever felt that? Yeah. So, simple trick. What you should do, take your phone, take a nice metallic copper container. Copper vessel will be there, copper, good conductors like copper. Take it over there, hello curiosity, and put your phone inside of it. There is a very good chance your phone might not be reachable. It depends on the signal strength and other things also, but most likely your phone will not be reachable. Try it out and see if it works. So this property is called as electrostatic shielding, also sometimes referred to as Faraday's cage. You might have wondered, sir, if there is thunderstorm and lightning outside, I might get struck by a lightning. So, I'm not going to stand outside. But what if I sit inside the car? Will I then be affected by the lightning? What do you think about it? Won't it be worse or will it be the best? Because your car is made of metal. So, do you think it will be really good to sit inside a car, or do you think it will be bad to sit inside the car? What do you think? Nice trick, Madhumati. Great. Sir, 11th gravitation really similar to 12th electrostatics? Yes, Shanmuga, it is very, very similar. So if you know one chapter, you can study the other chapter very, very easily. So actually, you will be much safer inside the car because of this Faraday's cage concept or electrostatic shielding concept. Okay, so this is the property which you are studying over here. It means that imagine you had a conductor, but there is a cavity inside of it. Cavity means hole, like in the teeth you have cavity, right? So there is a part which is just being scooped out. You cannot see it from outside, but there is a cavity. Maybe you have to do some MRI or some CT scan to find that cavity, that hole, that chunk which is missing. Okay, is it 2.8.3? I'll just have a look at it. 2.8.3 later on. Just 1 second, Krishna. Okay. Then, first of all, this property says that, listen, all the charges will always be on the surface. It will not even come on the cavity. See, some people think, sir, cavity is also a surface. No, sir. So, will charges come here? No. Charges won't come over here. Okay, charges won't come over here. The charges are always on the outside. Not just that, everywhere here, even this point or this point or this point, electric field inside is going to be zero and potential is going to be constant everywhere. This point, 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 this point. Everywhere you will see the potentials are same, field is zero. That is what it is saying. Not just that, imagine the conductor is not even charged. Imagine the conductor is not even charged, but let's say you have a cavity over here and there is some external charge somewhere outside. There is some external charge maybe over here. Imagine this positive charge is like a rock star, is like a superstar. the positive charges ends up attracting all the negative charges. It's like, imagine if there is a very, very hot pandu or hot champa, it will attract all the opposite people. Like for example, there is, imagine one superstar is there, maybe Taylor Swift. Okay, now Taylor Swift, everybody will go, but maybe some, I don't know, maybe some very nice heroine, pretty heroine is there. So all the pandus will go over here. So what is happening is, you will see all the pandus are going to go over here, negative charges are coming over here, and they have left their girlfriends who are basically a part of the atom, which is the nucleus, like so. So this electron left the positive charge. So this champa is alone, this pandu went here because there was a beautiful heroine over here. They all got attracted by it. And this will happen in such a way that in spite of all of this, electric field inside will still be zero, potential inside will still be constant. So this is always true even if this positive charge moves somewhere else. Even if this positive charge comes here, here, there, doesn't matter. Every time electric field inside is zero, preserved. So this means you have shielded whatever is happening from outside to inside. That is why the shielding effect. Is that clear, everyone? Did you understand this? Okay, so this positive charge has no effect whatsoever on inside. The electric field is always preserved to be zero. So a person sitting inside will never know there was a charge outside, because he'll be, oh, field is zero, field is zero, field is zero. I don't know whether there is an outside charge or not. You would never know if you are sitting inside. So you are shielding it. So you are shielding it. Okay. Shanmuga, let me tell you, which portion do you think is difficult? Let me tell you, everything is difficult until you start it. The moment you pick any topic and start it, then it is not difficult. Number one. Number two, start with some basic concepts of 11th standard. If you are not yet clear with it, watch my classes and then go to 12th standard portions. See, at least basic maths, all the lectures are freely available here. Number two, your vectors knowledge, and a little bit about Newton's laws or free body diagram, work per energy will help. In the next 1-2 weeks, I will be doing that also. So this basic topics, at least if you know, then it will be very easy for you to understand electrostatics. Then go to current, electricity, capacitors, potentials, all these things. Go sequentially, don't skip a part. It's best to go sequentially. Don't just directly jump to magnetism, because magnetism, you will see some similar things which were done in current and electrostatics repeating over there. Okay. So they're given some common examples of electric field and potentials. Whatever we have discussed, they have put it diagrammatically over here. Okay, 2.8.3 is it? Where is it? 2.8.3. Oh, this one. Thank you for pointing it out, Krishna. We missed this part. Thank you. Okay, so I think we did till this last lecture. So this is the one which we need to do. Okay, so now that we have done, I think almost all the properties of conductors have we done. Yeah, so we have to go to dielectrics and polarization. Yeah, before going to that, let's do section 2.8.3. Okay, potential energy of a dipole in external field. Let's do this. Okay, consider a dipole which is placed in a field, as seen that in electric dipole experiences no net force but experiences the torque which will tend to rotate it. Suppose the external torque is applied in such a manner that it neutralizes the torque and rotates it in the plane to some angle theta. Then the amount of work done is given by this P cos theta minus cos theta 1. Okay. And what they do is basically over here, the work stored as the energy as a system. We can then associate potential energy as inclination, blah, blah, blah. U has to be taken as 0, where the potential is 0 at 90 degrees. An explanation will be provided at the end of the discussion. And then they do all these nonsensical things and then they write, okay, so this is what the formula is, and they give some complicated equations. Okay, so let's have a basically look at this. All right. I will explain this to you in a very simple manner, guys. Imagine you take an electrical dipole. What is an electrical dipole, guys? We already studied this. What is an electrical dipole? It is nothing but two opposite charges separated by some distance, negative and positive. and then they develop a electrical dipole moment, which is nothing but the charge multiplied by the separation. Charge multiplied by the separation. It's a vector quantity whose unit is coulomb meter, whose unit is coulombs into the meters. That is what the electrical dipole moment is. Great. Now, ayo, there is no break, bacha. Where are you? Mango sorbet. You can, I know you want to eat mango, but it is not the season of mango now. So no break. NCERT line by line goes on continuously. Okay. So understand that. Now we also seen that when you place such a thing in some external electric field, when you place such a thing in an external electric field, let's say there is an electric field which is like this, electric field which is like this, then there are forces acting on it. This positive charge and this negative charge definitely experience electric forces, and these forces basically form a couple. So there is a couple force acting on it, where each force is nothing but the charge multiplied by the field, and hence there is a coupled torque. Which we have seen it in the last lecture as well, or the last to last lecture, and that torque is nothing but P cross E, is nothing but P cross that electric field which is there. P cross that electric field which is there. That is the torque acting on it. There is a torque acting on it. And we have seen that such a dipole loves to stay over here, aligned itself with the direction of the electric field when it is said to be in stable equilibrium. But if somebody disturbs this situation, say for example, you make this dipole go like this, or you make this dipole go like this, immediately the torque tries to bring it back. It tries to restore it, restoring torque. There is a restoring torque acting on it. This makes me feel as if there is a imaginary spring in it. Just imagine something wants to stay here. You move it like this. You're like, no, bring it back. Zoop. You try to pull it down like this. The torque brings it back here. Anything you do, it comes back. You do like this. The dipole bring it over here. Electric field is in this direction. The dipole experiences a torque and it will go back like that. It feels like there is an imaginary spring. This is that imaginary electrical spring. You can think of it like that. Are you able to visualize this? Mathematical derivation is not required, Shanmuga, but it helps you improve your understanding and the concept. That's all. Just don't try to by heart anything. Just try to understand why it is happening, just for one's sake. Once that concept is embedded in your head, it's all about applying it. Only for that sake you need to know certain derivations and not all the derivations. Yep, correct. So now, hence there is some kind of potential energy stored in it. Therefore, I can say, there is some kind of electrical, I would say there is some kind of electrical potential energy which is basically stored in a dipole inside a field. We want to find out how much this electrical potential energy is. So what they do is, you take the dipole and move it from one situation to the next situation, let's say the next situation, okay, like this, and the electric field is still like this only. This is the electric field, and let's say this is theta 1, let's say this is theta 2, okay, this is initial to final. So basically, in rotating the dipole like this, whatever work is done by that external force will go in changing the potential energy of that dipole system. Do you guys agree with this? If I do 10 joules of work, where will it go? In increasing that potential energy of that dipole. Fair enough. usually work was force into displacement. But for rotating bodies, what's the equivalent of force? Torque. What's the equivalent of displacement? Angular displacement. Hence, this work done externally, instead of writing force into displacement, it will be torque into the displacement. But this torque will be, the torque acting on the dipole to rotate it, and displacement will be very small because the torque will keep on changing. So I will put an integration symbol. So instead of F dot ds, it is torque into displacement, integration of it. Is that absolutely clear why we are using torque into d theta? Okay, because the torque might keep changing as the angle changes. You can see the cross product is involved over here. This is equal to change of the potential energy. That means U2 minus U1. U2 minus U1. Torque, like we said before, is nothing but PE sine theta. Is nothing but PE sine theta, and there is d theta over here, is nothing but U2 minus U1. So this will be also from theta 1 to theta 2. So let's put PE outside. That's exactly what they have done even in the derivation that you can see over here. Okay, PE sine theta d theta, and then they integrate this. Basically, then they integrate this. Okay, so what is integration of sine theta, guys? What is the integration of sine theta? It is minus cos theta. Minus cos theta, and then I will put theta 1 over here, theta 2 over here, and this is U2 minus U1, of course. So put theta 2 first, then put theta 1, then subtract them. So minus PE, and then you have cos theta 2 minus cos theta 1 is equal to U2 minus U1. You can keep this minus sign as it is. Later on we'll think about it. Now, do you remember this concept of zero reference potential energy? Where you can choose anything as zero. What matters is only the difference. See this over here only. Here, potential difference matters, not the potential value. So when you're going from a point to another point or situation to another situation, as long as the difference remains the same, what you assume as zero does not really matter. And you usually choose some standard situations as zero, which is convenient, and accordingly, then you basically define the energy at different points. Yeah. Is that right? Yep. Awesome. So, over here in this particular scenario, what we do is generally, we take this particular situation where the dipole moment is perpendicular to the electric field as our zero reference potential energy. Basically, the angle between them should be 90 degrees. That's what we take as zero. So using that concept, let me take one of the angle as 90. Let me take the other angle as some random angle. So let's say, I put, for example, theta 1 as 90 degrees, or basically pi by 2 radian. So in that case, U1 will be 0, which is our zero reference. And then let me substitute U2 as our potential energy for that particular in general angle theta. This is in general. So what will happen to this particular equation? Observe carefully. Minus PE is there as it is equal to something minus something. What will you have inside over here? Observe carefully. You will have cos theta, and here you will have cos 90. Here U2 will be U, U1 will be basically 0. This is what you will get. But we all know cos of 90 degrees is nothing but 0. So hence I will be left with nothing but minus PE cos theta is equal to U. To write it in a slightly better form, dipole moment is a vector, electric field is a vector, and I can see there is a product which involves cos with a negative sign. So why not write it as dot product with E? Why not write it as dot product with E? So this is our now new potential energy is nothing but P dot E, dipole moment dot electric field, dot product is involved but with a negative sign. So this is our formula. That is what they have derived, but in a very, very unnecessary complex manner. They have done the same thing minus P dot E, but in a unnecessary complex manner, guys. Is that okay? They have done the same thing, whatever is over here. Okay, minus P dot E. Is it absolutely clear? Yep. Very good. Awesome. Now, please remember one thing, that if you place that particular dipole, like this versus like this inside that same electric field, this is the case of stable equilibrium. This is the case of stable equilibrium. This is the case of unstable equilibrium. Why? Because the dipole moment is opposite. So any small disturbance will flip that dipole into this side. So it is highly unstable. Any small disturbance, zoop, that torque will pull it over here and align it like this. That's why it is unstable. This is stable because if you try to pull the dipole here, it will come back. So it is trying to be stable. It's trying to always come back over here. That's why this is unstable versus this is stable. Obviously, in any kind of equilibrium, 100% the torque is 0. In both the cases, the torque is 0. It's not like unstable means torque is not 0. It is 0, just that the nature of the disturbance and how it behaves thereafter decides the nature of the equilibrium. In this situation where it is stable equilibrium, obviously the angle between them is 0 degree. So cos 0 is 1, so it will be minus P. So the potential energy for 0 degree is basically minus P. When you are at 180 degrees, cos 180 is minus 1, minus into minus is plus. So potential energy will become plus P, So this is the maximum potential energy which you can get. That is why it is even unstable. This is the least potential energy you can get. Low potential energy means it will be stable. That's how you can also look at it. Is that absolutely clear, everyone? Understood? Clear? Awesome. Now there is one more part which they have mentioned right over here. Let me explain this part as well. See, when you take that dipole which has that negative charge and that positive charge and place it in an electric field like so. Okay, you place it in an electric field like so. Then we said that there is a electrical potential energy of that dipole in that external field, given by minus P dot E, That is what we have seen till now, minus P dot E. But this energy is the energy due to the interaction of this charge with the field and this charge with the field. Remember, there is one more interaction, and that is between this positive charge and this negative charge. They two together also have an potential energy. So just imagine, at the same time, there is also potential energy of just the dipole, and that will be given by your regular formula, which is K, Q, which is one is positive, One is basically positive Q, other is basically negative Q. Got it? One is basically positive Q, one is basically negative Q divided by R square. R is basically the length or the distance between those charges. So one is your positive charge and one is basically your negative charge over here. This is the potential energy of the dipole. So if they ask you by chance the total potential energy, the total net potential energy of the entire system, it will be this plus this. It will be the sum of both. So it will be nothing but your P dot E. It will be nothing but your P dot E over here, negative sign involved of course, minus P dot E. And this negative sign will also come over here. So minus, and you will have KQQ. You will have basically KQQ divided by R square. KQQ divided by R square, which is KQ square by R square. So this is the total potential energy. That is what exactly they have done right over here. KQ square by R square, and this is minus PE. That is your total energy. Is it clear? Understood? Sir, when disturbed in unstable equilibrium, it goes back into stable equilibrium. What would happen if to the potential energy stored in instability? That energy gets converted into kinetic energy because it was disturbed. Zoop! It is rotating. Rotational kinetic energy. So it gets converted into rotational. So then it will go like that. It will use the rotation and store into potential. Again, it will come back. It will keep oscillating. Basically, it is a problem of oscillations after that. In fact, in simple harmonic motion, there is a question where you have to find the time period of oscillation because potential energy and kinetic energy gets interchanged alternatively. Is that okay, Shanmuga? Okay. So what is the question that they have asked? A molecule has some electric dipole moment of this much order. Mole of this substance is polarized, okay, at low temperature by applying a strong field of this much. The direction of the field suddenly changed by an angle of 60 degree. Estimate the heat released by the substance in aligning the dipoles along the new direction. For simplicity, assume 100% polarization of the sample. So a molecule has this much dipole moment and it is getting polarized at some temperature by applying some field over here. Direction of the field is suddenly changed by an angle of 60 degree. So the question is how much heat energy is involved over here. So what you should understand is that imagine the dipoles were like this. Originally the electric field was also like this. Suddenly what they do is the electric field changes the direction by 60 degrees. The dipole still being there now experiences a torque. So it aligns itself in the direction of, the external field. So this is how it aligns itself. This was before. And in this process, obviously, the change in the potential energy involved goes as heat. The change in the potential energy basically goes as heat. In fact, that is what it has been also mentioned right over here. The loss of the potential energy, this must be the energy released by the substance in the form of heat to align the dipoles. So what you basically do is use our formula. Potential energy is minus PE cos theta. So delta U will be minus PE cos theta final minus PE cos theta initial. So if you notice this is nothing but PE is common, and then you have cos theta, let's say I, and minus cos theta final, that's all. So this is what you need to do. So the change of the energy is basically PE into difference of the cos theta, and this is basically going as heat as explained over here, as I have explained right over here. So they have just taken the difference, if you notice, right, over here. So this is nothing but dipole moment. Dipole moment was given already. Dipole moment was how much? 10 to the power minus 29. This was 10 to the power minus 29. And electric field was also mentioned. Electric field was 10 to the power 6. It was basically 10 to the power 6. And over here, you have to just take the difference of the two basically. Once when it was aligned versus once when it is shifted by 60 degrees. So it will be like cos 0 minus cos of 60 degrees. So cos of 0 minus cos of 60 degrees. So cos 0 is basically 1. This is basically 1. This is basically half. So 1 minus half is half. So this will be nothing but 10 to the power minus 29 multiplied by 10 to the power 6 into half. But remember one thing, this is heat per molecule. This is heat per molecule. When we want to find the total heat, so whatever you get per molecule, you multiply it by the Avogadro number for a mole. For a mole, it is nothing but 6 into 10 to the power 23. So whatever you get, 10 to the power minus 29 multiplied by 10 to the power 6 multiplied by half, you multiply it by 6 into 10 to the power 23. Solving this, you should get the answer as 3 joules. Solving this, you get the answer as 3 joules. Is it damped in ideal conditions also? In ideal conditions, it is not damped. In reality, it is damped. Ideally, if you take an ideal dipole, there is nothing for it to lose the energy with. But in reality, which is like this case, it is getting converted into heat. So that loss in that energy of mechanical energy is getting damped because of some external factors, friction, resistance, vibrations, thermodynamics, etc. And it will be lost to the surroundings permanently. Okay, Shanmuga, is that absolutely clear? So this is that example which is there in your textbook of NCERT. Cool. So all these properties are done. Shall we go to dielectrics and polarization? Everybody ready with this? Give me a quick thumbs up, everyone. Dielectrics and polarization. Shanmuga, it is not negative. The loss will be negative. The change in the potential energy, if it is negative, that means it has lost. So the heat released will be 3 joules. You will not mark minus 3. Don't mark minus 3. Okay? Because if I say a body had 7 joules of energy, now it has 5 joules of energy. So the difference of the energy is negative 2. What does it mean? It has decreased by 2. The potential energy has decreased by 2. So where did it go? As heat. So the heat released will be 2 joules. I won't say the heat released will be negative 2. If I say the heat released is negative 2, means heat is not released, heat is absorbed. Get the sign convention. Got it? Yep. Cool. Awesome. Thank you, Krishna. Thank you so much. Very good, Madhumati Krishna. Chitra, Suganya. Awesome. Paul. Awesome. Let's go to dielectrics and polarization. This is section 2.10. Dielectrics are non-conducting substance. In contrast to the conductors, they have no or negligible number of charge carriers. Recall whatever happens, the free charge move. Okay, this happens until in the static situation, the two fields cancel each other and the net field is 0. In a dielectric, this free movement of the charges is not possible. It turns out that the external field induces a dipole moment by stretching or reorienting molecules of the dielectric. Collective effect of all the molecular dipole moment is a net charge on the surface of the electric. It produces a field that opposes the external field. Unlike in a conductor, however, the opposing field so induced does not exactly cancel the external field, it only reduces it. Okay, and to the extent that the effect depends on the nature of the dielectric. To understand the effect, we need to look at the charge distribution of a dielectric molecular level. The molecules of a substance may be polar, non-polar. In non-polar molecule, the centers of positive and negative charges coincide. The molecule then has no permanent dipole moment. Examples are O2 or hydrogen. Because of their symmetry, have no dipole moment. On the other hand, polar molecules, which are the centers are negative charges are separated, such molecules have a permanent dipole moment. And ionic molecules such as this are examples of polar molecules. Okay, so we'll come to that now. Let's underline the keywords over here. Dielectrics are non-conducting substances. One important line over here, I'm underlining it for you. They have told you what dielectrics are. Now, next important point is, in dielectric, the field is not, it turns out that external field dipole moment by stretching. Okay. So, the next important phrase is over here. In a dielectric, the free movement of charges is not possible, very important, because it is not a conductor. An electrical conductor allows the free motion of the charges, but a dielectric, being a non-conductor, does not allow the free motion of the charges, because of which the external field induces a dipole moment by stretching or reorienting the molecules of the dielectric. The collective effect of the dipole moment is that the net charge, which produces a field opposing the external field, okay, which produces a field that opposes the external field, and it does not cancel, the induced field does not exactly cancel the external field, it only reduces it. It does not cancel, it only reduces it. That is what is mentioned over here. And then they go to the definition of polar molecules versus non-polar molecules. Okay, and the molecule may be polar or non-polar. A non-polar molecule is like oxygen, where you will see that the centers of positive and negative coincide. There is no permanent dipole moment. So oxygen, hydrogen are examples of it. And then they tell you about polar molecules, which has the centers of positive and negative charges which are separated, and examples of that are water and so many other such molecules. Hold on, I will explain everything to you. I'm just underlining all the important points over here. The positive and negative charges are displaced in the opposite directions. The displacement stops when the field on the molecules is balanced by the restoring force. The non-polar molecules thus develops an induced dipole moment. Okay, so a non-polar molecule. So the non-polar molecules thus develops and induces a dipole moment. The dielectric is then said to be polarized by the external field. We consider only the simple situation when the induced dipole moment is in the direction of the field and is proportional to the field strength. The induced dipole moments of different molecules add up, giving a net dipole moment of the dielectric in the presence of the external field. The induced dipole moment of different molecules give a net dipole moment in the external field, and also develops a net dipole moment but for different reasons in the absence of external blah 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 blah, and is applied the individual dipole moment tend to align when summed up. Okay, there is a net dipole moment in the dielectric polarized. Okay, then they give you for polar molecules also, like we discussed for polar molecules over here. They are talking about for polar molecules also develops a net dipole moment in the external field, but for different reasons. When there is no external field, the permanent dipole moments, when there is no external field, the dipole moments are oriented randomly due to the agitation. So when an external field is applied, the dipole moment tends to align with the field, and hence there is a net dipole moment. Okay. Thus, in either case, this is important now. Thus, in either case, whether polar or non-polar, there is a net dipole moment in the presence of electric field. And this formula has been written over here, where there is a constant to symbolize how much is the extent of the polarization. Okay. So let's understand all of this with a simple explanation now by your Captain Shreyas Sir. All the things which were written here, and here. Okay, all these things will understand it, whatever they have written over here as well. Okay, everybody ready for the explanation now? Let's understand it in a simple way. Yes, yes, it is very simple relationship, and yes, it is related to electrostatics. Correct. See, there are two kinds of molecules. One is polar and one is non-polar. So, just to go over here, where did they, yeah, here. Polar versus non-polar. Non-polar molecules are like, say for example, you take oxygen with oxygen. Okay, they do not have any net dipole moment because there is no charge separation as such. So the net dipole moment is basically zero. So because of which you say they are non-polar. They are non-polar molecules. There is no net dipole moment. But if you take the example of water molecule, there is a net dipole moment, and that net dipole moment, because it is there, they are said to be polar molecule. They are said to be polar molecules. This difference is clear. Net dipole moment 0, net dipole moment non-zero defines whether it's a polar or non-polar molecules, which you have already studied it in chemistry. Now, there are two situations. One for non-polar, one for polar molecule. Just imagine, so that is what they have explained over here. In a polar molecule, can I say for a polar molecule, if this is the polar molecule, okay, can I say that the negativity and the positivity is evenly spread, so the center of negativity and the center of positivity, they coincide? Whereas in a polar molecule, the negativity and the positivity is not spread evenly. Maybe one side is more positive, okay, as compared to the other side, because of which the effective positive charge is on one side and the effective negative charge is on other side, because of which only they are developing a dipole moment. Because the positives center and the negatives center, they don't coincide in this case, whereas here they are coinciding. They are basically said to coincide. The positive and the negatives coincide. Here they don't coincide. This affects the behavior of these molecules when you apply an external electric field. Now we are going to place these kind of molecules. Imagine you bring water or oxygen near some charge, near somebody's electric field. How do they behave? How will they get affected by it? Kamesh, for boards, yes, not for JEE, of course. JEE, you have to go beyond it. I have made a separate video on what you need to do. Just check it out, as NCERT and PYQ is enough for JEE on the JEE English channel, of course. Check it out. Imagine we have a basically non-polar molecule. Usually, when there is no field, what will happen is that the electron cloud, or that electrons will be spread like this, and even the positive will be over here only. So they coincide. There is no net dipole moment when there is no field. So I'll just put over here, no field, no dipole moment, and the positive and the negative centers coincide. But imagine somebody applies an external electric field. What will the electric field do on the positive charge? It will shift that positive charge maybe somewhere over here, because there is a force acting on it like this. What will it do on the negative charge? It will apply a force on the opposite direction. So our electron cloud which was there, maybe it will shift like this. Just think about it. maybe because of that force on that negative charge, it will shift like this. Now do you see the negativity is over here and the positivity is over here? Don't you see right now there is a net dipole moment? Now don't you see that there is a, now there is a net dipole moment? Net dipole moment in external field. In external field. Everybody understood how a dipole moment was created in external field? Got it? Till this point for a non-polar molecule? For a non-polar molecule? Okay. Now let's take the example of polar molecule. Let's take the example of polar molecule. For a polar molecule, what happens is, there are polarities, positive, negative, inside that substance, and they are oriented randomly everywhere. They are oriented randomly everywhere in that particular object. In that particular object, like this. That is what you will see. There is no particular system, okay, as such. And because of which, what can we say, my dear warriors? They are oriented randomly. So as an object as a whole, what would be the net dipole moment? The net dipole moment will be 0 for that entire object, although individual molecules have dipole moment. Although individual molecules have dipole moment, and this is when there is no external field. When there is no external field. When there is no external field. But the moment there is an external field, a magic happens. The moment there is an external field, there is some magic which happens. So let's say, for example, you applied an external electric field like this. This is your external electric field. What will happen? Each of these dipole moments will experience torque. Remember P cross E, won't there be a torque? Because of which, what will happen? These dipoles will then align themselves. These dipoles will then align themselves probably like this. Probably like this. Some dipoles may not have enough space, but still as much as possible, they will try to align themselves close to the electric field. Maybe they get obstructed at some places. Who knows, right? They might get obstructed. Maybe there is some problem everywhere. But you can see in general, they are all trying to be in this direction. Because of which you will see that the net dipole moment of that object is again not 0. It is existing. It is existing. It is like, as if this side has become negative and this side has partially become positive. Hence, there is a net dipole moment of that object. Is that clear? So, two different reasons. For a non-polar molecule, the cloud of the electron and the positivity shifts. So, there is separation, because of which there is net dipole moment. In case of a polar molecule, there is polarity, but they randomly orient and cancel each other. But in case of an external field, they will align themselves. So, dipole moment of the object exists in an external field of the object is created in external field, in external electric field. Is this clear? That is what they have been doing that in this particular paragraphs. They have explained polar, non-polar, what happens in non-polar molecules and what happens in polar molecules. So thus in either case, whether polar or non-polar, the dielectric develops a net dipole moment in the presence of external field. Is this clear, everyone? Very good. Madhumita, Krishna. Yes, Shreyas Sir, says Mukunda. Very good. Clear. Awesome. Awesome. Shreya, have you come here to count the number of students or to study? You tell me. Very good, Sukanya. Awesome. Now, whether it is this scenario or this scenario, point is there is a dipole moment which is created when you apply external field. Because of that, what happens is, you will see that there is an induced electric field which reduces the total electric field. Thus, you will see that the meaning of polarized means you have separated the charges, you have created a separation, you have polarized it. This side became negative, this side positive. This side became negative, this side became positive. That is called as polarization. Thus, the polarized dielectric, very, very important statement over here. The polarized dielectric is equivalent to two charged surfaces with induced surface charge densities like so. And the field produced by these surface charges opposes the external field. Hence, the total field in the dielectric is thereby reduced from the case when there is no dielectric present. And we should note that surface charge density does not arise. The surface charge density arises from the bound, not free charges in the dielectric. Okay. All right. We should also note that the surface charge density arises from the bound, okay, not free charges. Okay. So let me explain this whole concept to you now, what is mentioned over here. See, what does a electric dipole do? It creates an electric field around it. So let me show the electric field due to the dipole like this. It will create an electric field like this and like this. This is negative, this is positive. This is how the electric field lines look like, just like a bar magnet creating its electric field. You can see this is the electric field created by a single dipole. Now imagine there are more such dipoles. Just imagine there are more such dipoles. One dipole here and then another dipole over here. Just imagine this. Just for clarity's sake, I'm just putting over here the charges so that you understand what I'm showing. Remember, electric field lines always originate from the positive charge and terminate at the negative charge. So probably you will see one electric field line like this. Maybe you will see one field line like this and like this. But after that, it is going to be very difficult for the field lines. So it will be like this. Then it will be not be able to come back most likely over here because it's already crowded. So it will try to come back and then it will again go over here and it will come back here. Electric field line will come like this, electric field line will come like this, positive to negative. This positive will create an electric field, wants to go here, but it is too crowded, no place to join in over here. So because of which it will again go like that and it terminates over here. This will go like this and go like that. This will go like this and go over here. You can see the electric field lines are going like this in the backward direction. This is for two dipoles. Are you able to visualize it? Yep. Yes, Harish, correct. Now imagine there are multiple dipoles. Imagine that there are multiple dipoles like this. And very small dipoles placed very close in a big structure, in a big solid, in a big liquid, whatever, like this. Many such dipoles. How will the electric field lines look like for such a system? You will see probably very close the electric field lines will be like this, but overall it will probably look something like this. The electric field line is trying to go like that. Just imagine, I'm just extending this now for multiple such dipoles. It will go like this. Are you able to visualize this, guys? Everybody with me? Don't you see wherever the dipole is oriented, exactly opposite to that, electric field is being created. Electric field is created opposite to the dipole's orientation. Everyone clear till this point? Everyone clear till this particular point? Awesome. Now, imagine that we have a dielectric. Imagine we have a dielectric. So let me show that to you. This is our dielectric material. Some material is there. Let me create some copies of it. Okay, 4 situations I will show you guys. Situation number 1, situation number 2 in progression, and situation number 4. Situation number 1 is when there is no field. When there is no field, 100% the dipole moments will cancel each other out, and what you will see is that there is no net dipole moment. There is no net dipole moment. Everybody agrees till this point? The moment you turn on external field is turned on. External field is given. External field is basically given. That means, let me show these external electric field lines. What will happen? Dipole moments are created. I just showed it to you right over here. Be it polar or non-polar molecules, be it polar or non-polar molecules, wherever is the external field, same direction, net dipole moment is created. Everybody remembers? Any kind of polar or non-polar molecule. So what you will immediately see? What you will immediately see is that there will be dipole moments which will be created over here throughout that particular solid. Throughout that particular solid, like so. So there will be induced dipoles. I will say induced dipoles, and that is basically polarization starts. The moment polarization starts, what will that dipoles do? So many dipoles, what will they do? They will create an electric field opposite to the dipole moment, which means inside that solid, which has an external field and dipole moment in this direction, this is the net dipole moment in this direction, it will create its own electric field in the opposite direction like this. It will create its own electric field in the opposite direction. This will be then called as induced electric field. Induced electric field. And it opposes, what does it oppose? The external field. The external electric field. This was your external electric field. This was your external electric field. Everybody agrees till this point? It is opposing the external electric field. So inside this material, now you have a battle between the two. You have an induced field this way, and you have an external electric field this way. So what you will get is basically a net electric field in this direction. So what you will get is basically a net electric field in this direction. So this was your external field and this was your induced field, like so. Hence, the net electric field inside such a dielectric is always less than the external field. So whenever electric field lines pass through water, wood, paper, ceramic, stone, human body, wood, etc., which are all more or less like dielectrics, there is an induced field created because of polarization. So dipole formation is involved, and it reduces the field perceived inside the dipole. Inside the dielectric. So I can mention it over here. The net electric field is equal to the external field minus the induced field. Minus the induced field. Also, since the net electric field is always going to be less than your external field, there is a ratio which defines both of them. That net electric field is always going to be the external field divided by a number over here, K. This K is called as the dielectric constant of the medium. Dielectric constant of the medium. Dielectric constant of the medium. Some books also use the symbol like zeta. Okay, some books like even over here in NCERT, they have used this symbol, this zeta types, which is the characteristic of the dielectric. It's also called as electrical susceptibility of the medium. Okay, it tells me, how much, this is also called as electrical susceptibility of the medium, of that particular medium. It tells me how many times will the field reduce inside of it. If I tell you that dielectric constant or susceptibility is 2, that means whatever field enters, it will become half. If I say the dielectric constant or the susceptibility is 100, that means the field will become 100 times weak. If it was 100, it will become 1. If it was 1000, it will become 10. That is the meaning of this susceptibility. This depends on the medium. What does it depend on? The medium. Hence, you will see that the original permittivity, this was permittivity of free space, if you multiply it with susceptibility or basically the dielectric constant, what you end up getting is EM, which is permittivity of the medium. This is permittivity of that particular medium. Very, very important formulas that you are learning here. You can use X or K, one and the same thing. Okay, and the E net will be external divided by the susceptibility. Also, another important formula which you learnt over here was this. The net field is the external field minus the induced field. All these are the important takeaways. Clear? Shall we go ahead? That is what has been mentioned in all these paragraphs. Tell me, if you try to read on your own, I am 100% sure that you would be very, very confused. You would be very, very confused. One more thing about this particular line. We should note that the surface charge density arises from bound, not free charges in the dielectric. So what it means is that, see, when I show this negative and positive, it is not like, don't consider this like, okay, I had this solid and some positive charge traveled here and some negative charge was exposed here. No, that is not what it means. When I show positive, negative here, it says that it feels, because all the dipoles are oriented like this. So the positive is here, negative is here, positive is here, negative is here, positive, negative, positive, negative. It feels like everywhere the positive is towards the right, negative is towards the left. So it feels like the effective positive charge center is towards the right side and the effective negative charge is towards the left side. So it feels like the charges are separated. So when I show this plus and minus, it is not that there is an actual positive charge here and an actual negative charge here. Don't think of it like that. Don't think of it like that. It is just to say that it perceives or it feels like the positive charges and negative charges are being developed. So it is not the actual free charges. That is the meaning of it. Now it is crystal clear. Very good. Awesome. Great. So with this, we complete our basic electrostatics, Gauss law, potentials and potential energy. Let's move on to capacitors now. Okay, everyone ready for it? Let's move to capacitors right now. Is there a lecture scheduled right now by any chance on our channel? Anyone? No, right? Okay, thank God. Now, what is a capacitor and capacitance? Basically, a capacitor is a system of two conductors separated by an insulating medium, and conductors having charges q1, q2 and potentials v1, v2. Usually practice, we take q1 minus q, potential difference v. We shall consider only this kind of charge configuration. Even a single conductor can be used as a capacitor, other infinity. Conductors may be also charged by connecting them to two terminals of a battery. Q is the charge on the capacitor through this, and in fact, the charge on one of the conductors is the total charge of the capacitor is 0. The electric field in the region is proportional to the charge. That is, if the charge on the capacitor is doubled, electric field also will double, and because of which the potential difference will also be proportional to the charge, and that ratio is called as the capacitance of that particular conductor. Okay, first, a capacitor is a system of two conductors separated by an insulator. The conductors may have some charges q1 and q2 and the potentials v1 and v2, and usually we take v1 minus v2 as the potential difference between them. Okay, also they have mentioned even a single conductor can be used as a capacitor. Even a single conductor can be used as a capacitor by assuming the other at infinity. Okay, that is what they have mentioned. The total charge, very, very important, the total charge of a capacitor is always 0. But when I say the charge on the capacitor, what I mean is the charge on any one of the conductors. Also, they have mentioned the definition of capacitance right over here. The capacitance is the amount of charge on any one of the conductors divided by the voltage difference. This C is called as the capacitance of the capacitor. It is independent, very, very important. It is independent of the charge or V, as it only depends on the geometrical configuration, that is shape, size, separation of the system of the two conductors, as we shall see later. They have also mentioned what is the SI unit of capacitance, which is 1 farad, which is 1 coulomb per volt, and the symbol is also mentioned over here. Okay, some books also use that symbol. Okay, so let's understand what they mean over here by simple diagrams. Imagine I take a conductor and another conductor. Imagine one conductor is positively charged, another is negatively charged. Positive will have higher potential, negative will have lower potential. Agree, disagree, yes or no? This is just like saying, I have two containers. One has lot of water, one has very little water. They both have water of different amounts. Now what I do is, imagine I take this bucket and I connect it to this another bucket which has less amount of water. What will happen? Immediately this liquid which is there over here, it will begin to flow. It will begin to flow like this. Correct? It will begin to flow inside of this, and this level of water will begin to rise. This will begin to fall, and eventually this happens till both the levels are equal, till both the levels equalize, till an equilibrium is achieved. And you will see that they will have the same heights. These step-by-step processes, you can also repeat it for two conductors. Instead of connecting with the pipe, what you do is basically you take these conductors and realize one thing, that one has high voltage or high potential, one has low potential, and now you are connecting them with a wire. What will happen? Immediately from higher potential to lower potential, here water was flowing, here charges will flow. So what you will see is that there will be flow of charges. That means there will be electrical current inside this. Till when will this happen? Obviously, this will happen till their heights are same here. That means in this situation, the potentials are same. Till the potentials are equal. The potentials are going to be same, and then you will see there is a kind of an equilibrium which is achieved, and then there is no current in this, and then there is no current in this. Now in this case the current is 0. This is the step-by-step process when you compare it with fluid mechanics. Do you relate now this example with this example? Are you able to relate this example with this particular example, my dear students? Yep, correct. Very good. Now, in this process, when this water was flowing, imagine I had a turbine or some thing which can rotate. What will happen? That thing will begin to rotate. I can, draw some work out of it. This flowing water, it can do some work. It can rotate something. It can push some object. It can do some kind of work. Same thing when the current was flowing from high voltage to low voltage. If I put a bulb here, or if I put a fan here, if I put a motor here, if I put a resistor here, if I put some electrical device here, won't it lighten up, or won't it give energy? Won't it do work on that device? So isn't it like these two conductors which were charged are storing some energy, and we were using that energy to do some work? So they had some ability to do work, they had some capacity to do work. So capacitor stores that energy in that potential difference. So any two conductors which are charged, have some voltage difference between them, you will see they have ability to do work, they have capacity stored in it, they have some capacitance. And if you connect a wire via that device, that current will end up doing that work, electrical work, when that current passes. Is that clear? Yep, awesome. So this is how exactly a capacitor stores the electrical energy. It stores the electrical energy, and when connected with a wire, it does the work, and it can only do work only till potentials are same. So what is the difference between a capacitor and a battery? By the way, these two conductors, I generally symbolize them like this. So this is a capacitor. This is a capacitor. Remember, this is your battery. Both supply energy. But what is the difference between them? See, in case of a battery, it is the chemical energy. Some chemical reaction is there which gets converted into electrical. Work. Here, in capacitor, it is the electrical potential energy which goes into electrical work. That's one fundamental difference which goes into electrical work. Got it, my dear students? Yep, number one difference. Second difference is that a battery, usually maintains the potential difference as it discharges. It maintains the potential difference as it discharges. Here, you will see that the potential difference decreases as it discharges. So as the current flows, and you will see the potentials become equal, slowly the current goes off, the voltage difference also goes off, and it becomes 0. So that's why the voltage difference is not same, it keeps on reducing till they become equal. That's the main difference between a capacitor and a battery. That's very, very important. A lot of people do not know this. This is the symbol of a capacitor, that was the symbol of the battery. Now, even a single conductor is like a capacitor. You will be like, sir, how, sir? How is a single conductor a capacitor? How is a single conductor a capacitor? That's what they have mentioned over here. Even a single conductor is like a capacitor. How is that so? It's because you can assume that infinity is the second conductor. Remember, infinity is like the second conductor, And the property of infinity, if you remember, the potential energy, the potential is basically zero. The potential of infinity is basically 0 volts. So there is clearly a voltage difference between the two. Clearly there is a potential difference between the two. So if hypothetically one were to connect a wire from this to infinity, and maybe there was some resistor or something, 100% there will be current which will be flowing, and there will be some electrical work which will be done. So this is also doing some electrical work, some amount of heat is being generated in this resistor. So this electrical energy was stored even in a single conductor. So even a single conductor is going to behave like a capacitor. Is that clear, everyone? Okay. The next thing is where they define what a capacitance is, etc. They have defined what a capacitance is, etc. And here they have started with the other things. Let's discuss those as well. Okay. C small v is q. This means capacitor with large capacitance hold high potential difference plus strong electric field. Strong electric field can ionize the surroundings, blah, blah, blah. In other words, the charge of the capacitor leaks away due to reduction in insulating power of the intervening medium. Okay. If it can withstand without breakdown is called dielectric strength. And for separation for such conductors, okay, thus for capacitor to store large amount of charge without leaking, capacitance should be high enough. The potential difference is not large enough, hence the electric field should not exceed the breakdown limits. Put differently, there is a limit to the amount of charge that can be stored. In practice, a farad is a very big unit, and usual units are these. Besides its use in storing charges, capacitor is a key element for most circuits with functions as described in another chapter. Okay. So if there is a conductor here, there is a conductor here, this has some charge, this has some charge, maybe something else over here, this has more positive, this has maybe more negative, whatever. So if this has voltage V1, this has voltage V2, this has charge 1, this has total charge 2. So the difference between these two voltages is V, which is your potential difference. This is your potential difference. Now this is your general capacitor, general case. But if you talk of a more specific case, which we generally use in NEET syllabus, what we usually see is our capacitors will be something like this. One will have some positive charge, other will have exactly opposite amount of charge. So if this is plus Q, this will be minus Q. And if one is basically, for example, this is 0 volts, one is example 0 volts, this will be V volts. This will be V volts. Hence the voltage difference will be V. You can take V0, V by 2, minus V by 2, whatever you want to take. But main thing is the voltage difference is V volts, is basically V volts. And in such cases, you will see that the voltage and the charge, they are directly proportional to each other. So that ratio of the charge by that particular voltage is what gives you this definition of capacitance. This is nothing but your capacitance. You can see clearly what is the unit of capacitance. This is coulomb, this is volt. So it is basically coulomb divided by volt. Coulomb divided by volt. And this is basically called as a farad. So when you store 1 coulomb of charge, 1 minus 1 over here, across a voltage of 1 volt, the capacitance is said to be 1 farad. Capacitance is said to be 1 farad. So in a specific case, you will see that the total charge on that capacitor 100% is 0. But when they ask you what is the charge on a capacitor, they do not ask you the total charge. What they are asking you is basically on any of the plates, the magnitude of it. So hence the answer for such questions is always Q. Don't say, sir, will I give the answer as plus 2 coulombs or minus 2 coulombs? Always give the magnitude of the charge on any one of the plates or one of the conductors. That is what they mean. Is that clear? Yep. So the net charge is always 0, but that is not what they usually ask. When they ask you the charge on the capacitor, they are asking you on this or this. What is the magnitude of it? If it is +3, -3, answer is 3 coulomb is the charge on the capacitor. Okay, I understand that the net charge will be 0. So all these are important formulas, of course. So let's highlight them. Okay, now one more misconcept which is there. So all these things were being discussed, guys, right over here. If you notice, what is the unit, what is the formula, what is capacitance dependent on, and how does it change on different things. So let's discuss that as well. Since our capacitance is nothing but the charge divided by the voltage, is nothing but the charge divided by the voltage. Tell me what would happen if Q increases. What do you think will happen? Let's take these examples, Q, V and capacitance. Let's say the charge increases. What will happen to the capacitance? Tell me quickly. What will happen to the capacitance? Nothing. It will not change. In fact, if charge increases, numerator increases, voltage will also increase. Nothing will happen to the capacitance. In fact, somebody decides, let me reduce the voltage. Let me reduce the voltage. The numerator will also decrease, but nothing will happen to the capacitance. You will see the charge will reduce. This is what is explained over here. By changing the voltage or the charge, don't expect the capacitance to change. Capacitance is independent of Q or V. Don't think more charge means more capacitance. No. More charge means more voltage would have been applied, or less voltage means less charge will be stored on it. In fact, this capacitance which is there, this capacitance depends only on the material, the shape, the size, and basically the geometry. That means, how are these conductors? Are they spherical? Are they plates? Are they cubical? Are they conical? How much is the separation? What is filled in between them? That's what decides the capacitance. Is that clear, everyone? Yep, there will be no change. Correct. Very good. Many of you answered it correctly. Great. Now, the next part of this particular paragraph, this whole thing, discusses about a very important phenomena which is called as an electrical breakdown. And the charge of the capacitor leaks away due to the reduction in the insulating power of intervening medium. Okay, so they talk about the charge leaking away in that insulating medium, as a strong electric field can ionize the surrounding. So the maximum electric field that a dielectric medium can withstand without the breakdown of its insulating property is called the dielectric strength. For air, it is approximately this much. Breakdown is called as dielectric strength. For air, it is about 3 into 10 to the power 6. For a separation between conductors of 1 centimeter, the field corresponds to this much. Thus, for capacitor, then they say, for a capacitor to store a large amount of charge without leaking, its capacitance should be high enough. To store a large amount of charge without leaking, the capacitance should be high enough so that the potential difference and hence the electric field do not exceed the breakdown limits. Okay. So, what is the meaning of this particular statements? Let me explain it here only. See, or maybe down here, that is also okay. Imagine this is your ground, this is your tree, some buildings, okay, something, some mountains over here, okay. This is your ground, and these are your clouds. They keep floating in air, rubbing against each other. These clouds, when they rub against each other, it's like rubbing cloth with glass, or your hand with something, or your comb on somebody's head, or a plastic scale on something. What happens when you rub, guys? Put the answer in the chat box. What happens when you rub things? What happens when you rub things? Tell me. What do they develop? They develop charges, right? So because of the constant rubbing action, what might happen? Maybe these clouds also develop charges. Maybe these clouds touch each other, they exchange the charges, they rub more, they develop more charges. Imagine it so happens that some of these clouds have developed some charge. Maybe positive or negative. It could be anything. It could be positive or negative. It can be even negative. Don't think always positive only. Okay, maybe they developed some negative charge. Now, once they develop some negative charge, what will happen? There will be some electric field around it. Where will the electric field go? Well, Earth. Earth, we know, is basically our ground, and ground is basically 0 volts. Ground is basically 0 volts. This is 0 volts, this is negative volts. Clearly, there is going to be an electric field which is going to be developed over here. So maybe there will be electric field lines which will be developed like this. Electric field lines which will be developed like this. Do you guys agree with this? So there is this electric field which is developed. If the charges on the clouds increase, maybe this clouds, the charges have increased. Maybe on this cloud, the charges have increased in this particular region. Example. Okay. Chuma, I'm showing some random cloud. So what will happen? In that region, you will see more and more electric field lines will be there. More and more electric field lines will be there. Here the field will be very, very strong. Here the field will be very, very strong. And once the electric field becomes very strong, beyond a certain point, it can't withstand, and you will see that there will be lightning. What will you see? There will be lightning. And that's how that lightning from those clouds goes into the ground. Air was actually a bad conductor of electricity, isn't it? Have you ever heard of air conducting electricity? No, air is like an insulator. But how come air, which never conducts electricity, conducts these charges from such a high height to a ground level, and so much of charge, so much of voltage? Suddenly, it's because of the extreme high voltage difference creating a very strong electric field, and that strong electric field is beyond the permissible limits even of an insulator. Then that insulator goes into conduction. See, normally an insulator never conducts, but there is a limit for it. You apply a strong battery, insulator is like, no, I will not. It's like a determined person who is like a topper of the class. Come, let's go for a movie. No, I'll not come. Hey, come, let's chat, man. There is a very attractive girl there. No, I will not do anything. Hey, come, let's go eat this nice food chats. No, I will not. Come, let's play games. No, I will not. Come, let's do this. No. So you keep on pressurizing, and imagine so many kids. Hey, come, let's do this. Come, man, come, let's go here. Finally, we'll give up. Okay, come, let's go. So that breakdown happens. Same thing, even a non-conductor like air, the breakdown happens and lightning occurs. It's like strong electric field, a very high voltage difference creating that breakdown. Have you now understood this concept of lightning and how it is related to capacitors? So the same thing happens over here also. So when you have basically two plates of a capacitor, one is positive, one is negative, obviously there will be an electric field between them. It will be weak electric field. But if the capacitor is charged enough, and here also I can say there is low potential difference, there is small charge on it, but very high potential difference and very large amount of charge on it, then you will see that the electric field will also be very, very strong. This will be a strong electric field, and this strong electric field can lead to a breakdown. That is what they have told. That is what they have told. So you cannot expect that the capacitor to store unlimited charge, because there will be a breakdown point as well. So if you reach that breakdown point, that's it. You will see there will be a spark between those two plates, and that is the electrical breakdown. So for air, it is 3 into 10 to the power 6. The breakdown field for air is how much? 3 into 10 to the power 6. 3 into 10 to the power 6 volts per meter. That is what they say. So for a meter, you can't have more than 3 megavolts of voltage difference. If the voltage between two points separated by a meter exceeds 3 megavolts, sparks will occur. Sparks will occur if you exceed 3 megavolts per meter for air. That is what they have mentioned in this. Okay, so you need to avoid reaching such fields to avoid the leakage of charges in those insulators. Now let's talk about parallel plate capacitor and the effect of dielectric, and of course other things as well. Or else we can do one thing, we can probably do this in part number 3 maybe. Not sure how many, quite a few pages are there. Okay, let's finish it off. I think let's finish it off today. Let's finish it off. All right. Parallel plate capacitor. Just hold on. Just let us take a small break, guys, of 5 minutes, and let's come back. We'll do one thing. We'll take a break of 5 minutes. Welcome back, everyone. Yes, let's begin with the next part. And in case you have forgotten to like the video, please do that right now. Just a quick reminder. Yes, hello Krishna, hello Tanuja, looks like you are late. Yes, hello Abhi. Physics NCERT reading important, definitely. I hope you have seen this particular video which I have posted on the channel just a couple of days back. What is it that you need to do for NEET? Is NCERT and PYQs enough or not? Just check out that video. Okay, cool Abhi. Let's begin with the class and let's start. What is it? The parallel plate capacitor. So remember, just some time back I showed you over here that this particular capacitance depends on the material and the geometry. So based on how you have placed the conductors, how big, what is the shape size, you get different capacitances. Now there are three different shapes that you generally study, but main thing what you study in NEET is something called as a parallel plate capacitor, which is there in your NCERT, where you have two plates placed opposite each other. One is positive, one is negative, and they too store the charge, and there is an electric field between them, and that field stores the electrical energy. So two plates separated by a distance storing opposite charges is nothing but a parallel plate capacitor. That's what they have also mentioned over here. It's very obvious. A parallel plate capacitor consists of two plates, conducting plates separated by some small distance. They have charges plus Q and minus Q between them, and the distance is much smaller than the area of the plates. So we can use that the electric field will be roughly constant around that region. And then they have calculated the field outside as well as inside, and from that they have calculated the value of the capacitance for that particular capacitor. Okay, and then we go to the effect of dielectric. Okay, so see guys, imagine this. This is one plate, this is another plate, this has area A, this has area A, and the separation between them is basically D. The voltage across them is V. The charge over here is, let's say, positive. Charge over here is negative. So this is plus Q, this is minus Q. Okay, that is what they say. These are like charged sheets. This is one sheet, this is another sheet. So any sheet which is charged will create an electric field around it. So you can imagine that this sheet will create an electric field like this, as well as like this, and like this. And this electric field will be sigma by 2 epsilon naught. Sigma by 2 epsilon naught. You take the positive plate, the electric field is outward. Still, you take the negative plate, negatively charged plate, the electric field will be inwards. Just like here, the electric field was outwards, away from it. For a negative plate, the electric field will be towards that particular plate. So it will be something like this. What you will see is this electric field will also be sigma by 2 epsilon naught. Interesting thing to note is in this region and this region, which is basically outside. So this is outside, this is also outside. You will notice one interesting thing, and that is the electric field direction, whether it is this way here and the electric field here is like this. They end up cancelling out each other. Hence the net electric field outside is 0. Hence the net electric field outside is just 0. You can see the directions and magnitudes equal and opposite. Whereas if you go inside or between the plates of the capacitor, they are in the same direction. So the net electric field inside the capacitor is the addition of both these fields. So that means it is sigma by 2 epsilon naught plus sigma by 2 epsilon naught. That means the net electric field inside the capacitor is sigma by epsilon naught. So outside the capacitor, the field is 0. Inside the capacitor, the field is sigma by epsilon. Till this point, is everybody clear? Everyone understood till this point? Very good. Awesome. Now, what we do next is that using this electric field inside is sigma by epsilon naught. Sigma, what is it? What is this sigma? Charge per unit area. Sigma is nothing but charge per unit area. The charge which is there per unit area. So just put that instead of sigma. Charge per unit area. Okay, let me put it as it is. And what is electric field? Magnitude by definition for uniform field. See, if this is electric field, this is uniform, then magnitude wise it is dV by dr, which is the rate of change of voltage with respect to distance, which I can also write it as delta V by delta R. So voltage difference per unit length. So what is that voltage difference? It is V. What is that length? It is D. So can I not put it as V by D over here? V by D over here. Just check this out. Perfect. So let's rearrange it and see what do we get. Q is equal to, check this out, epsilon naught A by D and into V. A went on the top, D is below, V is on the top only, epsilon went on the top. Q is equal to epsilon at A D by D into V. But we already know Q is equal to C into V. Hence, what do I get? Therefore, what do I get? The capacitance by comparing is epsilon naught A by D. This is the formula which you are supposed to remember. Epsilon naught A by D. Is that absolutely clear? That is the capacitance of a parallel plate capacitor. Epsilon naught A by D. That is what they have got. Clear, my dear warriors? They have also got the electric field over here as Q by A epsilon naught, which is sigma by epsilon naught, which is exactly what we have got. And in the outer region, this was for the inside region. For the outer region, you can see it is 0. For the outer region, it is basically 0. Right? This is the capacitance formula. Fair enough, done, dusted till this point. Awesome, perfect, great. Now, what happens when you place a dielectric? The moment you place a dielectric, basically they have done some things over here to show what exactly happens. But mainly, I'll explain this, whatever they have written mathematically in very simple terms. All this over here. See, imagine there is a capacitor like this. There is nothing in between them, there is air. For air, the dielectric constant is 1. Roughly, it is like vacuum, it is like 1. So, if you have some charge which is over here, if you have some charge which is stored on that particular capacitor, there will be 100% some electric field between them, something like this, which will be like this. And that electric field, which is delta V by delta R, okay, that electric field which will be delta V by delta R, or I can also say it is nothing but charge by A epsilon naught. Charge by A epsilon naught. One and the same thing, guys. You can use dV by dr formula or sigma by epsilon naught formula. It's one and the same thing. And just keeping it on the sidelines. Now just imagine this was a capacitor where air was filled versus a capacitor which has some material filled between them. Some material which is filled between them. So there is a dielectric constant. There is a dielectric medium. There is dielectric medium which is filled between the plates of the capacitor. What does a dielectric medium do? A dielectric medium ensures that whatever external field was there, it tries to reduce it. So dielectric medium, so I'll just mention over here, a dielectric medium, what does it do? It tries to reduce the field. It tries to reduce the external field. It tries to reduce that external field. But here is the catch. I have taken that capacitor and I have still connected it to that battery. Just imagine, I have connected this particular capacitor to that battery. Has the battery's voltage changed? Has the battery's voltage changed? No. Has the distance between the plates changed? No. So hence delta V nor delta R can change. But delta V and delta R are still the same. But delta V and delta R are still the same. What does it mean? The net electric field is still the same. Still the same. How can this happen? How can this happen? How can the net field reduce but still it remains the same? There is only one way it is possible. Did you understand till this point? The dielectric medium should reduce the field, but that field which is there should not change also. There is only one way this is possible. If the old field, imagine if this old field was 20 volts per meter, the new field is still 20 volts per meter, but this field has come because it reduced from 30 volts per meter. Think like this, that maybe now there was more charge stored over here. There was more charge stored over here, because of which there was more electric field applied between them. But a dielectric always reduces the field, and it reduced the field to 20. So that's how it was able to maintain that field. Isn't it crazy? Just think about it. Just think about it. The old field was 20. The new field is also 20. But the dielectric medium should reduce the field. How is it possible? That means there was more charge which was created. So this 20 became 30 or 40 or 50. And then from that 50 it reduced back to 20, and it's like, listen, I am giving you the same field. If you still didn't understand it, I'll give a simple example. Imagine there is a country like Dubai, which has 0% tax, which has basically 0% tax. Okay, which has basically 0% tax. If you earn 100 rupees, what you get is also 100 rupees only. You also get 100 rupees only. But remember, there is a country, for example, where there is 50% tax. So ideally, if you earn 100 rupees, what you will get in your bank account is 50 rupees. But how do I earn still 100 rupees only? By making sure that 100 is remaining after 50% discount. That means now you have to earn 200 rupees so that you make the same amount of money as you made in that country with 0% tax. So you can see this is the increased amount. After reduction, it is same as before. Did you understand it? Is that absolutely clear? This is the simple way to understand it. So the old amount with 0% tax was this. To get the same amount but with tax, meaning because of the dielectric the field reduces. So you increase the original field because of the increase in the charge, and that's how reducing it you still get the same. You feel that, oh, the field did not change, but actually it had changed, but it has also been reduced. So that's why you don't see any difference. So now it stores more charge. So therefore it stores more charge for the same voltage difference. Because it has stored more charge for the same voltage difference, that implies the capacitance has increased. The capacitance has increased. Think of it that way. If imagine this new field, which is that external field, now becomes example, 50 volts per meter. So it reduces back to 20. So the dielectric was reducing it by how many times? The dielectric was reducing the field by how many times? We can calculate that. So the value of the new field was 20, the external field was 50, and the dielectric constant or electrical susceptibility was K. Therefore, the value of K will be how much? 50 by 20, which is nothing but 2.5. This is your dielectric constant in this situation. So the field has reduced these many times, but to make sure everything goes as per the plan, the charge will increase 2.5 times. So if the charge increases 2.5 times, that means the capacitance also increases by 2.5 times. So you will see that the new capacitance will be, in this particular example, will be exactly 2.5 times of the old capacitance. 2.5 times of the old capacitance in this particular example. Yep. Cool. So that's how placing a dielectric medium increases the capacitance by the dielectric constant times. That is what they have essentially done over here. Hence the new capacitance formula, which was epsilon naught A by D, you will put it as epsilon naught K A by D. So that K has come over here. That's all. Okay. As simple as that. So they have also mentioned it over here. The capacitance increases K times. Where have they given effect of dielectric? Yeah. This one. Thus, the dielectric, very important. Thus, the dielectric constant of a substance factor, this the capacitance increases from its vacuum value when the dielectric is inserted fully between the plates of the capacitor. That's what they have clearly mentioned right over here. The new capacitance is old capacitance into K. Okay, that's what they have clearly mentioned. An example, a slab of material of some constant has the same area of the plates of the parallel plate capacitor but has a thickness this much, where D is the separation of the plates. How is the capacitance changed when the slab is inserted between them? Listen to the question carefully. The slab of the material of a dielectric constant K has the same area as the plates of a parallel plate capacitor, but the thickness is not complete, where D is the separation between the plates. How is the new capacitance between them? Now they have done it, using a different technique over here, but you don't have to go with the technique. I'll tell you, in NEET, just directly use my formula, which is like a trick, which will help you solve such kind of questions. What is that trick? Let me tell you first, before going to this question. Whenever you have different slabs which are placed between let's say this is K1, then maybe over here there is K2, okay, something like that, and so on and so forth. Then what you do is, each of these slabs will have their own thicknesses, T1, T2, T3, etc. And let's say the area of the plates of the capacitor is A. The new capacitance will be epsilon naught A divided by, usually it was D, right? Now don't put D. It will be D1 plus D2 plus D3 plus like that, as many terms as possible. And what is there over here? Is first term will be D1 but by K1, or the thickness 1 by K1. So that instead of D, I have put T over here. It's okay. Just one thing, I'll put it as D1. So it will be D1 by K1. Then next one will be D2 by K2. Next will be D3 by K3, and so on and so forth. So use this formula whenever you have multiple slabs in between. It is very easy to solve. See, when you have completely filled material, then that new capacitance we know it is epsilon naught A by complete material is filled, so complete distance by K, which comes out as epsilon naught A, K goes on the top divided by D. This is when it is completely filled. When it is completely filled. Here it is not completely filled, incompletely filled, then you use this formula. D1 by K1 plus D2 by K2 plus D3 by K3. As simple as that. So in this particular problem also, use my formula. It will become very, very easy for you to solve, because this is the trick. This is that trick to solve the problems in the NEET exam very quickly. Or else if you go by NCERT method, you will spend a lot of time. So epsilon naught A divided by, in this situation, the capacitor looks like this. The complete distance between them is d, but the material is only filled by 3/4 of a distance. This is where that material is filled, whose dielectric constant is basically K. The remaining gap is of air, who has a dielectric constant of 1. So this was 3d by 4. Obviously, this is d by 4. So over here, I will have 3d by 4, whole thing divided by K, plus d by 4 divided by 1. d1 by k1 plus d2 by k2 plus d3 by k3. Here there are two materials, only two terms are there. That's all. That's the answer, guys. You can simplify it if you want. So you can see this is epsilon naught A divided by d by 4, which is obviously common. Okay, d by 4, which is obviously common. So 3 divided by k plus 1, of course. So 4 goes on the top. Epsilon naught A 4 divided by d, and take the LCM. So 3 plus k divided by k. So k again goes on the top. So 4 epsilon naught A k divided by d and 3 plus k. That is the new capacitance. That's it. That's what exactly they would have also got. 4k by k plus 3 and all of that. So you can see epsilon naught A by d is the old capacitance. So 4, and you can put epsilon naught A divided by d separately and k divided by 3 plus k. This is your old capacitance. So that's why it will be 4 times k times c naught divided by 3 plus k. That is exactly what they have got. 4 times k times c naught divided by 3 plus k. Got it? Isn't this method much simpler, guys? Nice trick. Super, Harish. Very good. Understood? Awesome. Clear, Madhumati. Very good, Chitra. Tanuja, Pratibha. Great, guys. So don't use the NCERT method. Now, combination of capacitors, one is series, one is parallel basically, and then they have started with the examples. So it's very simple, guys. In resistors, what happens? Current is the same. In resistance, current is the same. In capacitors, charge will be the same for series. Okay. And in parallel circuits, voltage is the same. Here also, capacitors, voltage is the same. That's the main thing. So what they have done is basically combining them. Thus in the series combination, charges are same. Thus in the series combination, the charges on the two plates are basically same. And the total drop is the sum of the voltage drops. The total voltage drop is the sum of the voltage drops. So solving this, you get 1 by C is 1 by C1 plus 1 by C2. So for series capacitors, the formula is like parallel resistors. For capacitors in series, the formula is like parallel resistors. 1 by R1 plus 1 by R2. As simple as that. And this can be extended for more capacitors also. So in general, you can see, in general, the total voltage is the sum of voltage across all capacitors, and the total capacitance is basically 1 by C1 plus 1 by C2 plus 1 by Cn. That is the reciprocal of that. Is that okay? Everyone? As simple as this. This is exactly opposite. Whereas for parallel capacitors, one placed besides each other, the voltages across each capacitor will be the same. So the charges will be different. That's all. So it's mentioned clearly over here. The same potential difference is applied across the capacitors which are arranged in parallel circuit. And you will see that the total charge which was there, it will get distributed on these multiple capacitors. That's why the charge will be Q1 plus Q2. So in general, if there were many capacitors, the charge on the effective capacitor will be the sum of the charges. Here the charges add to give you the total charge. In series, the voltages add to give you the total voltage. It's exactly opposite. Whereas the capacitance formula, is just like series resistance. When capacitors are in parallel, the formula is like series resistance. So formula wise they are opposite, concept wise they are same. Concept wise they are same. I'm so glad, Harish, you found this series useful, and just keep attending, that's all. See, even if you don't attend live, that's okay, but mainly you should watch it within 1 or 2 days maximum. Whenever these lectures come out, you have to immediately watch it off within next 1-2 days. Don't keep a backlog of 2-3 weeks or 5 weeks or like that, because the more faster you do, then you will be in sync with whatever is going on with the problem solving, mock tests, etc. Because once the series is over, once I complete almost all the chapters of 12, you'll be seeing that we'll be doing PYQ series, we'll be doing mock tests, we'll be doing additional problems, we'll be doing revision, right, one shots. So you need to be prepared for that, or else you will be still having these backlogs, and then I would be ahead, then you will miss out on all those things. So ensure that even if you are watching this session recorded now, maybe after a month or so, you try to cover up your backlogs, minimize it, and be in sync with the live classes as much as possible. That's why attending live is the best, because then you have no backlogs. But when you attend recorded, make sure you are covering it up within 1 or 2 days, else that will create more backlogs. Alright, so they have given some capacitors over here. There is a 4 capacitors network, and they are basically mentioning that they are connected to some voltage, equivalent capacitance, the charge on each capacitor, etc, etc. So over here, can you see this capacitor is in one branch, this and this are one after the other in the another branch. So 100% these three together are in one after the other manner, which means they are in series. That branch is in parallel with this branch. That is like obvious. So that is exactly what they would have also done over here also. First they would have taken parallel, then they were connected in series, then they would have connected in parallel, and then they would have found out the answers. So let's do it for the sake of it. Say for example, if you just consider these 3 capacitors, because they are in series, the equivalent combination will be 1 by C1 plus 1 by C2 plus 1 by C3, that is 1 by CS. What are the capacitors? Everything is 10. So 1 by 10 micro into 3 times, that is 1 by CS. Therefore, CS is 10 micro by 3 farad. The effective combination is 10 by 3 microfarad for these 3 in series. Their combination with this one is in parallel. So the net effective capacitance between A and B will be, take this 10 by 3 microfarad and add it to this 10 microfarad. So 1 plus 1 by 3 is 2 by 3. So 10 into 2 by 3, which is 20 by 3 microfarad. 20 by 3 microfarad is the effective capacitance. Because they are in parallel, you add. When they are in series, you use the parallel resistors formula. So 20 by 3 should be the answer, which is also right mentioned over here. Is that right, everyone? Clear till this point? Clear till this point? Yes. $40 by 3. Did we do some wrong or something wrong? Everything fine, right? I think 40 by 3 should be wrong. Pratibha, just check that out. Okay, great. Now the question is, what is the charge on each capacitor? See, if this is the equivalent capacitance, the total effective charge on the equivalent circuit, which will be Q is equal to CV. C is basically 20 by 3. Voltage is nothing but 500. So basically 2 5s are 10. and 3 zeros. So 10 into 10 to the power 3 divided by 3. But this is in micro. So you have to also put micro over here. So it will basically become 10 to the power minus 3, and then that 0 will also be there. So basically 10 by 3 millicoulomb. 10 by 3 millicoulomb will be the total charge. 10 by 3, yeah. 10 by 3 will be the total charge. Perfect. Now, oh sorry, I think I made a mistake over here, guys. So sorry, my bad. While doing this, happens when you take classes for a long time. 1 plus 1 by 3, I said 2 by 3. So sorry, guys. It was 4 by 3. My bad. So this is 10 by 3 plus 10, and this will be nothing but 4 by 3. So hence it will be 4 by 3 times of 10 microfarad, which will make it 40 by 3 microfarad. Perfect. This was the total effective capacitance. Now, once I get the total effective capacitance, we can find the charge on each capacitor. The total effective capacitance was 40 by 3 microfarad. So the total charge on the circuit, which is capacitance into voltage. Remember, the total voltage was 500 volts, which will be 40 by 3 into 40 by 3 micro into basically 500 volts into 500 volts. 4 5s are 20 into these 3 zeros, and micro is 10 to the power minus 6 divided by 3. So this will become 20 by 3 millicoulomb, the total charge on the circuit. The total charge on the circuit will be 20 by 3 millicoulomb. But that charge obviously is not there on this or on this. It is on the total circuit. So it will first think of it like that. The total circuit was a combination of this capacitor and this capacitor in parallel. So if I split it, I will have now two capacitors, one here and one here. As a whole, they had a total charge of 20 by 3. As a whole, they had a charge of 20 by 3. So this capacitance was actually a combination of a 10 microfarad capacitor here and this capacitance, which was 10 by 3 microfarad over here, which was connected across 500 volts. Is that right? That is what actually this circuit was. Okay. So what will be the charge on this guy? What will be the charge only on this particular guy, on this lower one? That charge on this lower one, the lower one is called as C4 basically. So Q4 will be C4 into the voltage. C4 is nothing but 10 micro. Voltage is nothing but 500. So hence it will be nothing but 5 into 10 to the power 3 into 10 to the power minus 6, which means it will be 5 into 10 to the power minus 3, which is 5 millicoulomb, which is basically 5 millicoulomb on this capacitor. Whereas on this capacitor, which is over here, the charge would be this capacitance, which was in series, into voltage, which is 10 by 3 into, this was micro again, this is micro, into voltage, which is 500, which is 10 by 3 into 10 to the power minus 6 into 500, which is how much? 5 into 10 to the power minus 3 divided by 3, which is 5 by 3 millicoulomb, which is basically 5 by 3 millicoulomb. Remember, whatever is the charge on this capacitor, which was actually a combination of these three capacitors in series, each one of them would have the same charge. Because remember, when you take series capacitances, the charges are the same. When you take series capacitances, the charges are the same. That's what I have told. The series, the charges are basically the same. So just use that concept. Hence, all the capacitors on the top, this one and this two have the same charge. That's how you do it. One is this one, another one is that one. Is that clear? So In series, all the ones on the top have 5 by 3 millicoulomb. Clear, my dear warriors? Understood? So the ones over here have 5 by 3 millicoulomb, 5 by 3 millicoulomb, 5 by 3 millicoulomb, and this one over here has 5 millicoulomb. This one over here has 5 millicoulomb charge. That is the final answer. Great. Now we are coming to the final concept, which is basically the energy stored inside a capacitor. We are coming to the final concept, which is the energy stored inside a capacitor. What is the final energy stored inside a capacitor? See guys, when I started capacitors, I told you this explanation where it is like two buckets with different water levels. You connect it with a pipe, it can do some work. So I said that since water can store energy, same way conductors charged with different amounts have a voltage difference. So when connected with a wire, the charges flow and it can produce current which can further completely do some work. So there is some energy stored inside any capacitor. We want to know how much energy is stored. That is the whole concept. So there is electrical energy stored inside a capacitor, which we are going to see right now. In order to calculate that energy, there is a small derivation which they have done, okay, right over here. And they have also found out the energy per unit volume and all these things. So let's just see how this exactly comes. Let's understand it carefully. I will not show you those slides because then it will be confusing. Imagine there is right now no charge on the capacitor. There is no charge on the capacitor. That means there is also no energy inside the capacitor. There is no field also. Now consider a random moment, consider a random instant at some instant of time. There is some charge Q over here, there is some minus Q over here. You are taking some charge from this side to this side, and that charge is basically dq across some voltage difference which is at that moment, I call it V, across V potential difference, across V potential difference. Slowly you take a charge, place it here, so the charge will increase over here, the charge will become more negative over here. And this is the process of charging. Slowly you keep on charging, dq, you keep on taking away the charges and keep on placing it here until that capacitor becomes fully charged. It becomes fully charged. It is a steady state. And the final charge on the capacitor, here it is plus Q, here it is minus Q. And the total voltage difference is capital V. Total voltage difference is capital V. This is the process of step by step charging the capacitor from here to here to here. Let's talk about this particular scenario. In this scenario, by adding this charge, you are increasing the energy. This increases the energy stored by du amount. Why du? Because small charge is increased. So the energy incremented will also be du. How much will that energy increase be? It is the same as the work done to move that dq charge across a potential difference of basically V, small v. Whatever work you do is getting stored. If I lift a box, I do some joules, it gets stored in that box as gravitational energy. If I move this charge across a voltage, it gets stored as electrical energy. So hence that dW work done is du, but this work done by external force, remember we have seen it in electrostatics, it is the charge multiplied by the voltage difference. Here the charge is dq, the voltage difference is small v. That is basically du. Do you guys agree with this? Work done is charge multiplied by the voltage difference. Perfect. Now what is our next step? Wait a minute. I know one more thing over here. You know what? For this particular situation, also keep in mind, always charge is capacitance multiplied by potential difference at any point. So any instant of charge is C into voltage. Therefore, V is nothing but Q by C. How about using that over here? Therefore, dq, instead of V, I will put it as Q by C is equal to du. dq into Q by C is equal to du. Move it slightly. So du will be Q dq and 1 by C will come over here. Q dq, 1 by C will come over here. I know what should be my next step. Obviously, integration. This is the constant. When there is no charge, there is no energy. How do I know that? Here. No charge, no energy. That is the lower limit. The upper limit is when there is full charge, there is full potential energy. When it is fully charged, there is final energy stored in that capacitor. So, U minus 0 will be 1 by C. This will become Q square by 2 minus 0 square by 2, substituting the limits. Therefore, what I get is U is equal to half Q square by C. Half Q square by C. But we can do it in more forms. Charge was capacitance into voltage. So hence it will become half C square V square by C. Therefore, I can also write it as half C V square. Also, we can do one more thing. This half CV square, I can write it as half CV multiplied by V. I know what is CV. CV is nothing but the charge. So it will become half Q into V. So in general, I can say that the electrical potential energy stored in a capacitor has three different ways of writing it. I can write it as half CV square. I can also write it as half Q square by C. I can also write it as half QV. One and the same thing. This is like power is V squared by R or I squared R or voltage into current. One and the same thing. This is the energy stored in the capacitor. Is that absolutely clear? This particular formula. Now what they do in the next thing, okay, they have done the exactly same thing, guys, over here. Okay, whatever I have written down, the same limits, they have explained it in a, I don't know, whatever way they want, but it's the same thing. And the next part over here, they have found the energy stored per unit volume. So what does that mean? Let me come to that. See, we took a capacitor, there was some voltage difference and there were some charges over here. There was some electric field between them. There is also some separation between them, D. There is also some area between the plates. We saw that there is energy stored in the capacitor. We find one more term which is called as energy per unit volume. Energy stored per unit volume. Energy stored per unit volume. This is called as electrical energy density. Electrical energy density. What is this electrical energy density? It is energy stored per unit volume. If you notice the unit, it will be nothing but joules per meter cube. If you take a small volume, in that volume, how much energy is stored? That is the electrical energy density. So how much will that energy density be? The symbol for that is rho u. It will be energy stored upon the volume. Now, the energy stored inside the capacitor, I just told you it is half C V square. And the volume is nothing but area into the gap. Area into the distance is the volume. But wait a minute, capacitance We know it is epsilon naught A divided by D. Okay, voltage square divided by AD. I know one more thing. AA just got cancelled, so it will become epsilon naught by 2D square. Epsilon naught by 2D square. So I can just write it as epsilon naught by 2. Epsilon naught by 2. AA got cancelled. I hope you can see that. Area got cancelled. So I have been left with V and D over here and square it. But wait a minute, what is voltage by distance? It is nothing but electric field. So it is electric field. Hence, the electrical energy density formula is half epsilon naught electric field square. This is the electrical energy density formula. Half epsilon naught E square, which is what they have also mentioned over here. Energy stored per unit volume of the space. This is that formula. And this one is the energy stored in the capacitor. Cool, everyone understood these formulas? This formula as well as this formula. Shall we go ahead? Okay, very good. Krishna, Sukanya, Madhumati, awesome. Tanuja, Paul, Pratibha, great. So let's do a question over here which is mentioned. They are saying that there is a capacitor of 900 picofarad charged by 100 volt. How much energy is stored by the capacitor? The capacitor is disconnected and connected to another similar capacitor. What is the new energy stored of the system? These kind of questions are very, very common in your NEET examination. So first of all, let's do the first part of the problem, which is this part. How much energy is stored by the capacitor? Over here, you can see it's a capacitance of 900. So the initial energy stored using half CV square formula will be half. Capacitance is 900 pico. So let me just still put pico. Voltage is 100 square. So 9 by 2 is 4.5 or 450. Pico is 10 to the power minus 12. 100 square is 10 to the power 4. So you can further write it down as this will become 10 to the power minus 8. And this will become then 10 to the power minus 7. Yes, 45 into 10 to the power minus 7, which you can probably write it as 450 into 10 to the power minus, or basically write it as 4.5 into 10 to the power minus 6, which is 4.5 microjoules. 4.5 microjoules. That is the first answer. Yeah, 4.5 microjoules. That is the first answer that we got, which is perfectly fine. That energy is very, very small. That shows capacitors can't store joules and joules of energy, but only a very small amount, which is okay. Great. Now comes the next part. You are connecting it to another identical capacitor. So then what happens? See, this capacitor also had some charge stored in it. So what is that charge stored? It is C into V. 900 pico, which is 10 to the power minus 12, into voltage, which is 100. That will make it 9 into 10 to the power minus 8, which I can write it as 90 nanocoulombs. 90 nanocoulombs. Yes, 90 into 10 to the power minus 9. Perfect. 90 nanocoulombs. Is that okay, everyone? Those of you did not get it, okay, no issues. This is 9 into 10 to the power minus 8. I can write it as 90 into 10 to the power minus 9. So that's why 90 into This is nothing but 90 nanocoulombs. That is what I have written it down now. Okay. Now what happens is, this 90 nanocoulombs which was there on 900 picofarad capacitor, side by side there is another capacitor just 900 picofarad, but there is no charge on it. The next step, I'm just connecting them together. Don't they look like parallel capacitors? Don't they look like parallel capacitors when you join them? When they are basically joined, it feels as if they are parallel combination. So I can treat it like a single capacitor. 900 plus 900 will make it 1800 picofarad. And because the charge can't go anywhere, it will still have 90 nanocoulomb of charge. 90 nanocoulomb of charge because it is conserved. The charge has to stay there. Isn't it amazing? Perfect. So what is the energy stored now? I can say half Q square by C formula, half charge square, which is 90 square, nano is 10 to the power minus 9, square it, divided by capacitance, which is 1800, pico is 10 to the power minus 12. Now do the math. 1 by, I have 9 square over here, I'll keep it as it is, into 10 square, which is 10 to the power 2, and over here 10 to the power minus 18. Here 18 I can write it as 2 into 9, and this is going to become 10 to the power minus 10. So one of the 9's cancel and it will just become 9 by 4, I believe. This will make it 10 to the power minus 16. This will become 10 to the power minus 10. So it will become 10 to the power minus 6. 10 to the power minus 6. That's it. 9 by 4, which is nothing but 2.25 microjoules. 2.25 microjoules. Is that right? Everybody till this point? Now once I have this answer, what will I do? I'll go back to the question. What was the question? What is the electrical energy stored by the new system? Exactly. So I got the answer. What is the electrical energy stored by the new system? It is basically 2.25 microjoules. Is that right, everyone? Awesome. Awesome. Now, if you notice, the original energy was 4.5. The new energy is 2.25. So 100% there is a difference between the energies. So if you calculate the difference between the energies, the final minus your initial energy, final, which was 2.25 microjoules, versus the initial energy, which was 4.5 microjoules, 100% there is a difference between them. How much is it? It is negative 2.25 microjoules. This negative symbolizes there is a loss. So this loss means that there is some heat lost as 2.25 microjoules in this process. In this process of connecting these capacitors, some amount of energy is lost. Yes. Its negative signifies loss. Heat loss is there. These kind of questions are also asked in your NEET examination. Is that absolutely clear? Everyone with me? Yep. Perfect. Perfect. Oh, that's it. That's the end of the chapter over here. So we have completed in 2 parts this particular amazing chapter of electrostatic potential and capacitance. This completes our entire electrostatics, Gauss law, voltages, energies, capacitances, and after this sometime we will be having PYQ and problem solving session also. But for now, make sure you are attending all these NCERT line by line series of your 12th standard physics chapters, because it's also important from your 12th standard board perspective, especially even if you are in Karnataka board. Remember, all the Karnataka board students, also very, very important, because you have your state board syllabus exactly aligned with your NCERT, and very similar portions and syllabus is there, obviously for NEET also. So make sure you are attending it. Okay, NCERT is a must. Thank you so much. God bless you all. See you in the comments for the waiting for the next chapter. All right, I want to see all your comments down there. Bye bye. Have a great time.